100 kilometers above the Earth's surface lies an invisible frontier, the edge of space. This is the Kármán line, the boundary between our planet's atmosphere and what lies beyond. What does it take to cross that line? To date, some 450 cosmonauts, astronauts, taikonauts, the names all mean the same, have crossed that unseen line. Cold War test pilots to begin with, then geologists, engineers and scientists of one kind or another. Mission specialists now come in all sizes and nationalities. Even politicians and cashed-up tourists have gate-crashed the space party. But how do you earn an astronaut's wings? As Chris Hadfield, the first Canadian to walk in space, has said, an astronaut's life is one of preparation and simulation, and training and support on the ground, and anticipation and visualization. And very, very seldom, almost never, is an astronaut's life about flying in space. In one sense, the key to becoming an astronaut is simple: brute force. But selection for space is an exhaustive process. Astronaut candidates must be fit, physically and mentally, to endure the rigors of training. High intelligence is essential, while bravery is a useful character trait. The current crew of astronauts have trained for work on the International Space Station, while others are working towards missions yet to come. They have one thing in common: they all consider themselves lucky.
I never planned to become an astronaut. I mean, I knew that it's a very small likelihood, and so as a scientist, I knew the statistics, meaning like, okay, if I try to become an astronaut, it probably won't work out. So for me, applying with ESA to become an astronaut was not as much a thing of me believing that I would become an astronaut, but more trying to give my dream a chance that I had, that I knew I was always looking forward or trying to see, do I have a chance to actually go there?
It also helps if you know how to use one of these.
I find my background as a pilot very helpful, just in the way that I've previously been taught how to follow procedures, for example, as a pilot, communication methods, working together in a team in an international environment. All of those sort of skills are very useful in this job.
Of course, I had expectations before I started. But the job as an astronaut is so unique. I think it's difficult to have a realistic sense of what to expect. So certainly some things have been what I expected. I mean, the excitement, the uniqueness, the wonder of human spaceflight is exactly what I thought it'd be. Other things, of course, have been different simply because it's such a unique world to train for a mission.
Astronaut candidates should expect a 2-year period of training and evaluation. Learning to live and work in extreme environments comes right at the start. Movie buffs will recall Key Largo in Florida as an isolated place for Humphrey Bogart. Now it houses NASA's Nemo facility Aquarius, training astronauts for both the ISS and future asteroid missions. Other unwelcoming environments used for isolation and team building include the Sagruta Caves in Sardinia, Italy.
The ESA Caves mission that I was a part of a few years ago, where I spent a week living underneath the ground in a gigantic cave system. The 2 NASA NEMO missions that I've been able to participate in. I mean, all these things are fantastic opportunities in and of themselves. And just having those opportunities without going to space would be fantastic. But so to have them and then to go to space as well is just really it's what makes this job so unique and so fantastic.
Of course, spaceflight training is not easy. I think that's clear. I mean, for 3.5 years, you have to travel almost every 3 weeks. You fly over the Atlantic, you're in different training locations. You spend about 5% of your time at home. And if so, maybe then just a weekend here or there. So it's a challenge.
Training takes us all around the world into every center. I've already done 2 or 3 orbits around the world, but just in a plane going from NASA to Russia to Japan and back to Europe. So it's already, the training as an astronaut in itself is already rewarding. I mean, it's already the dream job. And even better, it gets you to a flight in the end. So there's no time to be bored. There's no time to think too much about what you're doing. Every day you're busy, every day is a good day, and that's going to continue until the flight.
Use the ladder. Okay. Careful, and I'll just follow you. And we'll sit down there.
Space training in Europe begins at the European Astronaut Center in Cologne, Germany, where trainees learn the essentials of maintenance and repair of onboard systems.
You would be asked to actually either remove or clean or just inspect the filter. We would need to close the line.
They also continue their basic EVA training in another unfriendly environment, underwater.
In general, the training at the different locations varies quite a bit. First, there's the technical side, which means like we're training in Japan on the systems that Japan supplied to the space station. In Russia, we're training on the Russian segment of the International Space Station. In the US, we train for the US side. And at ESA, we train for Columbus and ATV, which are the modules that ESA supplied to the space station.
Next, the candidates move on to NASA's larger Johnson Space Flight Center in Houston, Texas, for extensive EVA training.
Training at the JSC is always very busy because we do many different things and it's a huge facility, so we're moving all the time from one building to the other. Like here we are in the building 9, where we have a replica of all the American modules of the space station. So in this building we train for the space station. Some of it is daily operations, some of it is actually off-nominal operations like emergencies. Like in these mock-ups in this building, just yesterday I did a 5-hour emergency simulation with my crewmates, with our full crew complement of 6 people of Expedition 42. And that of course is not something that you would call daily operations. That's something that we really don't want to happen, but we train it a lot because emergencies would put us as crew in danger.
Here we go.
HCN 1.2.
The great thing about being trained on emergencies is that it gives you a state of mind. Having the knowledge, having the training can help you in any situation, in any condition, just like it happened to me during my EVA. It was an unexpected emergency that we had not been trained for, but because you have received training that it's all encompassing, it gives you the state of mind where you look forward to the solution rather than focusing on the problem.
EVAs, extravehicular activities, sound routine enough. But spacewalks, as we know them, are among the most dangerous duties an astronaut must carry out. Preparation and safety-conscious planning are critical.
Behind me you see a lot of equipment which is related to the airlock operations in case of a spacewalk, so we train this here as well. But there's also another completely different facility, which is the Neutral Buoyancy Lab. That's a huge pool, and in there we train for spacewalks underwater.
Neutral buoyancy training tanks are in place at ESA's Cologne facility and at Star City in Moscow, but JSC has the biggest.
EVA training is fantastic. It's physically difficult. It's one of the most challenging parts of the training, but it's also one of the most realistic. When you're in the pool for 6 hours, you get tired, but at some point you really think you're on the ISS, you look around you, and there's a structure everywhere. Sometimes you even get disoriented because that's what happens in space. It's like a 3D labyrinth of technology. It's a maze of technology.
There is so much going on here because we not only train space station, but robotics, spacewalks. So it's a very complex training system, and it's very exciting to be part of it.
I think one of the hardest parts of the astronaut's job is to retain all this different information over the 2.5-year period from being assigned to actually launching. There's an awful lot of information on the Soyuz, on the space station itself, robotic training, EVA training, the list goes on. So to try and retain all that, the way that they do that is just by having refresher training really along our path to launch.
JAXA, Japan's space agency, trains astronauts in the operation of the country's ISS contribution, the Kibo experiment module, with its space exposure platform.
So this is nominal.
I guess it has a very Japanese flavor to it. I mean, the content and the way the content is presenting and delivered is pretty much standardized. But of course, the instructors are Japanese. They have that very polite, very kind Japanese way about them.
In Saint-Hubert, Quebec, the Canadian Space Agency's Mobile Servicing System Operations Complex schools astronauts in using robotic arms on station.
Here's a station at scale, and here's a robotic arm also at scale. It moves and we can plan our maneuvers. As you can see, the main challenge is to not hit anything while you're moving this arm, because all you got really when you're working, if you come here, there's this workstation. You got a couple of camera views to work from. You got your hand controllers to move the arm, and you get some computer displays and a bunch of switches here on the left. That's all you got. So you really got to think ahead how you're going to maneuver this arm without crashing into anything, because of course that would be a very bad day on orbit.
Experience the past like never before with History Hit's award-winning original documentaries and ad-free podcasts with our expert historians like Dan Snow, Susanna Lipscomb, Lucy Worsley, Mary Beard, Tristan Hughes and myself, Matt Lewis. Sign up for an exclusive discount using the link in the description and embark on your historical journey from the wonders of ancient Egypt and the life of Anne Boleyn to the rise of Napoleon Bonaparte and the discovery of Shackleton's Endurance. Get history wherever, whenever, exclusively on History Hit.
Star City near Moscow in Russia was the birthplace of manned spaceflight. It remains a key training center where all ISS assigned trainee astronauts go through the program.
When you first start in Star City, you immediately feel like you're part of something bigger than just your own personal history, because your personal story, because you see people who've been here since the beginning. There's even supposedly Yuri Gagarin, his wife, is still living here, even though she's very old, she's still living in the vicinity. So you just cross people in the corridor, and they've known all those guys, and I was just a kid, and those guys were already in human spaceflight. So you try to learn as much as you can. You try to do your best for the technical side of the job and try to interact as much as possible with the people, because they're so experienced that they have a lot to give you.
Expecting the unexpected is a basic training principle, like landing off course after the mission or touching down in the Siberian tundra.
Добрый вечер.
As NASA has no manned flight hardware of its own at present, the agency purchases seats on Russia's Soyuz spacecraft. All astronauts must be trained on the Soyuz systems, which poses a problem of its own. Everything is, of course, in Russian.
All the documentation's in Russian in the Soyuz spacecraft, and of course all the conversations in Russian as well, which is the reason for us having all of the Russian lessons during our training flow.
Not only must you know the Russian language, when in Russian spacecraft, you must also wear Russian spacesuits.
When the Sokol space suit actually pressurizes, things do become much more difficult to work because you're kind of fixed in your seat in a very rigid location, and it's hard to bend your arms and bend your fingers in fact. So even just sort of reading the board documentation can be quite difficult. But hopefully you won't be pressurized when you do a normal descent. Hopefully the spacecraft will come down without any problems and your spacesuit will be much softer, which makes it easier to move.
Here in Star City, I'm using most of my time in the Soyuz simulator together with my commander. Suddenly it's starting to feel a lot more real, you know, when you're sitting in the Soyuz and you're really going through the whole launch and landing sequence. You can feel that you're getting close to the date, and it's very, very exciting.
It's a very well-oiled machine, this flow to launch, and I'm confident that, you know, by the time every astronaut flies, you're really ready to go. You're prepared in every way.
As things stand, an astronaut bound for a 6-month mission to the ISS needs up to 5 years training, a requirement which will, in all likelihood, be intensified for future missions to deep space. The ISS will probably be used as a long-duration astronaut training facility for missions to Mars and beyond.
We are also all people that are selected to be able to get along with each other. That's kind of like the way you select astronauts nowadays for long duration space flights. You really want to have people that are balanced, that are easy to get along with other people.
So much of our work up there is determined by the visiting vehicle traffic, and that's a very dynamic phase because we're not quite sure exactly which vehicles are going to arrive when.
I got 18 centimeters.
And these vehicles bring up a lot of science, they bring up a lot of hardware that determines when the EVAs are done, and also they of course determine the robotics activity that goes on to capture the vehicles. So when you're not quite sure what the visiting vehicle schedule is like, you're not quite sure exactly what science and when it's going to be done on board the space station.
One 6 months increment for the whole crew is around 300 experiments, out of which there's 55, 60 for ESA. So there's a wide array of domains like medicine, technology, material science, fluid science, everything you can think of. We're trying to make the most of the conditions in space and the microgravity to get results that wouldn't be possible to achieve on Earth.
So one of the things I've learned is you just have to be extremely flexible, and we get trained on how to do tasks that may be planned 6 months ahead of our mission and maybe planned 6 months after our mission, so that should there be some flex and those activities fall within our increment, then we're trained and we're ready to do those as well.
There's some leftover smell.
Whoa. It's not good.
Not good.
Looking out of the window is really one of the most fantastic experiences that you can have from the International Space Station. Our Earth is so beautiful, And yet when you look outside, you see that the atmosphere that surrounds our Earth is so thin. It's merely like an eggshell around an egg. It's so fragile, and the vulnerability, the fragility of our planet is very, very visible from on Earth. You see this blue ball, and then above nothing, just black, absolutely nothing in this immense universe. And I would hope that more people would be able to fly to space, more maybe of our politicians, decision makers would be able to fly to space and really see the vulnerability of our planet, so that we can finally start doing something about climate change.
Videos. So the way it installs this needs to be in the flush. Dual lock to get to the more forward. So cut.
We're just so prepared. All the emergencies, all the possible failures, we train them over and over and over again. So we're supposed to be able to handle any situation. We sat in the simulator hundreds of hours. We know the systems inside out. So there's nothing really that we fear, I think, on the technical side.
Even with all that training, astronauts are well aware of the dangers of space flight. Riding a rocket full of explosive fuel, living in an enclosed environment with a thin sheet of aluminium between you and hard vacuum, solar and cosmic radiation, bullet-like micrometeorites and space debris. Then there is the threat of onboard fire or mechanical failure, and to cap it all off, the fiery return to Earth. There is, however, one problem that returning astronauts cannot avoid, and that's gravity.
When you get back home, of course, I will always remember this was the same for my first flight or for my second flight. The moment they open up the hatch and you feel this fresh, cold air coming into your capsule. This is really something. And you're out there, of course, in the steppe. You have this real soil kind of smell that you have. It's really feeling fantastic. And then they get you out of the capsule. And the first thing, of course, that you want to do is to contact your family, your friends, saying, I'm all right, everything is great. We will see each other tonight. And then you just want to rest and to sleep because you're so tired, of course, from this long day of coming back. And also the gravity is really then having an impact on your body. You can't, it's difficult to stand up. It's everything that you have to lift. It's hard, it's difficult. And this takes a couple of days. But after a couple of days, of course, you recover well. We have a very good recovery program here at our European Astronaut Center. Our people are really very focused on getting the astronaut back up to the level as he was before the flight as soon as possible. And then, of course, it's again, after a while, business as usual.
I'm reaching the end of my career and I'm being able to do a last flight and really, again, put at work for myself, but also for everybody else, all the knowledge and know-how that I've acquired during this year. It's a very great opportunity, and I'm really happy that I've been assigned for this.
There is another way of crossing that unseen line on the edge of space, by paying your own way as the ultimate tourist. A number of wealthy individuals have already done so. Soon enough, it will become cheaper and accessible to the ordinary mortal, provided he or she can pass the medical.
You know, when our test pilots and wonderful team that run Virgin Galactic say that we're ready to go, then I'll be ready to climb in and be the first passenger as such, to go to space and to become an astronaut, and from there, hopefully, thousands of people will follow me.
Launching payloads into space is no straightforward matter. Historically, rocket launches have been used as the proverbial swords into plowshares. Missiles designed to carry atomic warheads now send satellites and probes into the solar system. Ironically, it's one of the few exploits mankind undertakes that doesn't occur in nature. Rocket science is all it's cracked up to be. Bringing together the mathematical, engineering and mechanical skills required to design, build, test and successfully launch a rocket into space is a mammoth technical undertaking. So many countries and corporations have the capacity for launches nowadays that they appear commonplace.
Zero.
Only the keenest science geeks seem to watch them these days, unless, of course, something goes wrong, and then everyone is hooked. Space launchers fall within several categories, based on their payload or cargo weight and where it needs to get to. The unsung heroes are the commercial satellite delivery systems, providing light and medium lift capability to low Earth, polar or geosynchronous orbit. Many countries such as Argentina, Iran, North Korea and Ukraine boast their own homegrown systems. Even New Zealand, in a joint venture with the US, is developing a budget CubeSat launcher called Electron. The Soviet Union, first to harness its ballistic missiles, has several workhorses like the Proton rocket family, the Rokot, Zenit, Dnipro and sea-launched Volna systems. Ukraine in its current form inherited some of these rocket systems after the Soviet breakup. Like the Proton, these systems use highly toxic fuels. They will be phased out by 2030 and replaced by the Angara rocket system, which is both environmentally friendly and modular in construction to save launch costs. The Angara rockets are designed to put payloads ranging from 3,800 to 24,500 kilograms into low Earth orbit. The Russian Soyuz rocket, designed in the 1950s, has proved to be the most reliable rocket system ever flown. Upgraded to version 2, it will continue to operate alongside Angara. The Russians are also looking to develop a replacement for their aging Soyuz TMA spacecraft, with several designs already on the drawing board. Japan has its Epsilon satellite launcher, which can lift 1.2 tons into orbit. Their H2 continues to evolve, the B variant delivering cargo missions to the ISS.
Ignition. And liftoff. Liftoff of the HTV on a journey to the International Space Station.
ステーション補給機コウノトリ4号機を搭載した H2B ロケット4号機は平成25年8月4日午前4時48分46秒に種子島宇宙センターから打ち上げられました。
India's ISRO space organization has developed a range of vehicles for delivering satellites, either to polar orbit with the PSLV or geosynchronous with the GSLV Mark II. India has big plans for space development, one of which is to build a man-rated capsule. The Chinese Long March series of rockets has made steady progress and powers China's manned space program. Even they are becoming environmentally conscious as well. The Long March 5 heavy thrust cluster rocket, with a loading capacity up to 25 tons, is by far the largest carrier rocket China has.
Compared with previous rockets, the biggest difference is the non-toxic propellant in hydrogen-oxygen engines and LOX kerosene engines that will not pollute the environment. And we applied serialization, unitization and modularization to design and manufacture.
Another major player in launch capability is the European Space Agency ESA, with its facility at Kourou in French Guiana. The Vega launcher, developed by ESA and the Italian Space Agency, continues to operate for light payloads. The real European success story, however, is the Ariane 5 heavy lifter, the workhorse for ESA and the CNES. But it too will shortly be replaced by Ariane 6. Currently under development, it will use components in common with the new Vega C rocket.
Ariane 6 will reduce the cost of our launch service by 50% compared to today. So you have to realize that in just 4 years, we are reducing the cost of a launch service in Europe with 50%. And that is, of course, a major step. And if you think about Ariane 6 in a double launch configuration, we are able to offer a price which is really, really attractive, also in comparison with the competition. So the situation that we will have with Ariane 6 and Vega C will be exactly the same in terms of what we can launch as we have today with Vega, Ariane 5 and Soyuz. We can launch every satellite with these two launches in the future. It is very clear that the international competition is getting more and more intensive. This is very clear, especially from the American side. We can see that there is a systematic, let me say, aggressive approach of the market to gain market share by American suppliers of launch services.
When NASA, intent on pursuing the Orion and SLS deep space system, relegated low Earth orbit to the private sector, the commercial floodgates were opened. The United Launch Alliance took over the existing NASA hardware and services and now operates the venerable Atlas V, along with the Delta II and heavy lift Delta IV systems. It's now developing the Vulcan rocket for future expansion.
Main engine ignition, 2, 1, and liftoff. Liftoff of the United Launch Alliance Delta IV Heavy rocket carrying the NROL-37 mission.
The
The Vulcan Centaur vehicle will be a high-performance, lower-cost, best-value vehicle. We're going to maintain our mission success history that we've had with Atlas and Delta. So we've got two main engine suppliers, Blue Origin with the BB4, which is a natural gas-powered engine, and we've got the AR1 from Aerojet Rocketdyne, that is the RP1 configuration. Both of those teams are making good progress. We've been through CDR with the Blue Origin engine. We've been through PDR. They're both on a plan to get to engine testing this year, and they're both on a path to support our late 2019 launch date.
With that mission now opened up to commercial ventures, many companies are rushing to build better, safer, and, most importantly, cheaper rockets. Two private service suppliers for NASA are Orbital ATK and SpaceX. These are the first two contracted by NASA for current ISS resupply payloads and planned manned transfer missions. Orbital uses Minotaur rockets, which are in reality the MX Peacekeeper ICBM, which was never fully deployed as a result of disarmament treaties. Orbital has modified these rockets to carry scientific payloads. Their heavy payload launcher is the Antares 230 and 232, which can lift 8,000 kilograms into low Earth orbit, including the Cygnus spacecraft. With the Falcon 9, Elon Musk's SpaceX company is working on the principle of recycling or reusing launch systems to make launches cost-effective. They can now return the main launch stage back to Earth and land it safely, to be refurbished and ready to launch again. Working on their heavy lift Falcon, which will be able to lift 54,000 kilos into orbit, or 13,600 kilograms towards Mars, and then return to the launch site for reuse. Even the Falcon Heavy, however, will be dwarfed by the upcoming NASA Space Launch System. It will tower over everything previously seen, with the capacity to put 130,700 kilograms into orbit or send 52 metric tons into deep space. Its first task will be to fly the Orion crew capsule and a probe to the Galilean moon Europa. Sending humans into orbit is another matter altogether. Here, launchers have to be incredibly reliable and able to lift very heavy payloads safely. In other words, they have to be man-rated. The only two man-rated capsules at present are the Chinese Shenzhou and the Russian Soyuz TMA. Unsurprisingly, they look very alike. The Russians, however, are looking to the future and a crowded commercial market. Their Soyuz has successfully flown over 120 missions, but a new, cheaper capsule called Federation is underway. It will carry up to 6 cosmonauts and will be competing against NASA's Commercial Crew Development Program, which has Boeing and SpaceX delivering cargo and soon astronauts to low Earth orbit. Aerospace giant Boeing's space capsule, the CST-100 Starliner, is to ferry astronauts to and from the International Space Station.
Starliners go.
When you're sitting in the capsule on top of a rocket and the final moments of the countdown are happening, it's exciting. It's like being on the top of that roller coaster when you're a little bit scared, but you're really pumped because this is what you've been working for all your life, taking that next step into exploration.
We're over 1 kilometer. Truck deploy. Trucks look good.
California-based SpaceX is developing its Dragon capsule to carry crew to low Earth orbit and beyond. The crewed version of Dragon would carry up to 7 astronauts to the orbiting lab. Blue Origin is a strong competitor to both contractors, but its sights are on the tourist suborbit segment. They too have designed their rocket to return to launch for reuse, and their capsule, the Blue Shepard, can hold 6 paying customers.
Shepard has cleared the tower.
There you have it. There it is, 70,000 pounds of thrust pushing that crew capsule.
When the B3 engine remains on, the booster continues to space.
The drogues are out on the crew capsule. There go the mains. And touchdown of the New Shepard crew capsule. From what we can tell, that was a nominal in-flight test of our escape system. And again, all astronauts on board would have had a pretty exhilarating ride.
There you go. The booster speed, that tail fire has got second shot. Beautiful. Wow.
There it is.
Touchdown.
What an extraordinary test and a tremendous final flight for both craft.
Their main rival will probably be Virgin Galactic or Vulcan Aerospace with their air-launched systems. Sierra Nevada's Dream Chaser is a small space plane designed to carry 7. The spacecraft is based on a NASA concept vehicle from the 1980s called the HL-20. Having failed to secure a NASA contract, Sierra Nevada has teamed up with Vulcan and European interests to further develop a version of the Dream Chaser. Advances in aeronautical engine design have led to the Sabre.
We're actually at Reaction Engines test site at B9. What is very significant about this is that we are in the process of testing a very, very important development in aerospace propulsion, which is a pre-cooler, a device for cooling the air entering the high-speed engine so that the engine can continue to operate pretty much as normal. This means that we're going to be able to fly at speeds of Mach 5 pretty easily in the future.
It is in effect a rocket engine burning hydrogen and oxygen. That in itself is not unusual, but whilst in the atmosphere the oxygen is taken from the air, cooled to liquid temperatures and fed directly into the combustion chamber, once outside the atmosphere, the engine resorts to the liquid oxygen carried on board, like a conventional rocket engine. Skylon will be powered by 2 Sabre engines and operate like a conventional aircraft capable of flying directly into orbit, transporting 15 tons of cargo into space and returning for a runway landing.
We're looking at a revolution in transportation equivalent to the jet engine, and access to space, access to anywhere in the world within 4 hours is on the cards. Once you've got access to space on that basis, that's the stepping stone to anywhere in the universe, and a very exciting future for the human race.
Although government contracts are lucrative for these private companies, many firmly believe tourism is the way to fund future space development. For those cashed-up civilian tourists, Space Adventures team has designed a circumlunar mission using a unique combination of existing and flight-tested Russian technology. The combination of the Soyuz spacecraft and the lunar module will provide ample living space for your approximately 6-day journey and the fuel required for you to leave low Earth orbit. Perhaps the most ambitious is Elon Musk's SpaceX interplanetary transport system, helping make humanity a multi-planet species. The initial design objective of the vehicle is to launch a variety of missions to Mars and other destinations in the beyond Earth orbit portion of the solar system. The large payload capacity of the launch vehicle, with the ability to place 300 tons into low Earth orbit, places it into the super heavy lift class. The ITS launch vehicle's first stage is designed to be reusable, following a return to the launch site and vertical landing after each launch. What's new on this vehicle is full reusability of even the second stage and the spacecraft as well. Cheap, safe space travel for all is just around the corner. The International Space Station is without question the jewel in the crown of low Earth orbit. Observation post, research lab and classroom all in one. But many other assets orbiting Earth are even more important to our everyday lives, delivering communications, weather observation, global positioning and resource management, and the list is growing every year. Chances are you are watching this program via satellite in one way or another, either transmitted directly or indirectly to your television, iPad, laptop or phone. In other words, you're using technology once considered science fiction. Pushing the envelope, technology must keep up with demand. More data, more reliability and real-time connection. Space-destined hardware and technology are on the cutting edge of science, often introducing new methods of gathering scientific information. Demonstrator missions are regularly sent up, flying new engineering solutions to prove the hardware in situ, even without a specific goal in mind.
Technology goes through a whole development cycle, which we call the seamless chain of innovation. We start from the idea and we work along to develop it through our work in the labs, through the work of industry, and especially of small and medium industries, which are the vectors of innovation. But at the end, you need to prove that it works in the real space. And in order to do that, we use these missions that can take the risk of flying unproven technology and demonstrate to the larger missions that they work.
Research laboratories focusing on the next generation of space hardware are dotted around the globe. The UK's Space Gateway Harwell campus, the ESA RAL Advanced Manufacturing Laboratory, supports cutting-edge research and development.
The purpose of the laboratory is basically to assess and pre-screen candidate materials and processes for future space missions. So this will guide ESA, as well as the space community, in focusing their technology investments in the right area.
The lab has extensive on-site testing facilities, such as the ISIS neutron source, the Diamond Light Source synchrotron, and the UK's Central Laser Facility. This year will bring the first launch of a satellite using the small GEO platform, Hispasat 36W1. Small GEO, a telecommunications platform accommodating a wide range of payloads and missions, has been developed in Germany in a public-private partnership between ESA, OHB, and the operator Hispasat.
It indeed, because Hispasat and ESA were able to join forces, that we were able to develop a satellite with such a level of innovation. On the one hand, a new platform with a new satellite prime contractor, on the other hand, a payload embarking also a high level of innovation. And altogether, this satellite has been developed, is going to be flown, and we provide very innovative services. So end-to-end, the level of innovation is very high, and indeed, separately, neither Hispasat nor ESA would have been able to undertake such a complex development. With the small GEO, what we have tried to achieve was really to develop a new product in the low end of the telecommunication market. And at the same time, this new product would allow a new prime contractor to become a prominent player of the satellite telecommunication market. That's the OHB, which is the prime contractor of this satellite.
This is a class of satellites that only have electric propulsion on board, which is a high-efficient system that allows achieving important mass savings. So we are able to put in space a satellite with a similar capacity of a full chemical one, but with much lower mass, which means less launcher cost, compatibility with more launch vehicles. And again, this translates in advantages for the operators who have at their disposal more efficient technical solutions for their mission. But it's very flexible, so it can also be used for other geostationary applications.
Another scheduled event in the telecom area is the launch of EDRS-C, expected by the end of the year. EDRS-C is also based on the small GEO platform and will be the first dedicated satellite for EDRS, the European Data Relay Service. It will be the second element of the Laser Relay's Space Data Highway. Low Earth satellites encumbered with line-of-sight communications can beam their data upward to geosynchronous satellites via laser, which can then transmit the signal to ground stations at any time.
The small GEO program is just the first step for OHB. OHB has already sold a number of other telecommunication satellites, and indeed this is the start of a product line that will evolve over time, like any other product lines of the other prime contractors operating in the satellite telecom market.
Another area of research has been in cost and time effectiveness in developing satellites. This has led to the CubeSat, several of which have flown in space. Measuring just 10 by 10 by 10 centimeters, these small cubes or nanosatellites have become extremely popular, opening up new possibilities for a wide range of groups previously unable to access space.
We are a small group of students with 2 professors and 2 coordinators, and we had 52 students who did the master's thesis on this project.
It's a great project for the students because it's the occasion to apply practical stuff and not only the theoretical stuff they have learned at school.
Our satellite is the telecommunication satellite. We use the D-Star protocol for the radio amateurs to communicate around the world.
This is really a special moment when we can see that finally the people is installed on the platform that will carry it to space on board the Soyuz launcher.
So it's a great feeling to be here in Kourou, in French Guiana, with the satellite almost in space and normally ready to roll.
Using off-the-shelf technology, CubeSats have been launched from the ISS and piggybacked onto other satellite launches. They will soon be deployed to Mars, asteroids, and further afield. GPS is used every day by people on the ground thanks to global positioning satellites from the United States. But GPS is not the only system in orbit. Russia has its GLONASS constellation, China has its own Beidou system, and Europe is building the Galileo network.
The initial services is a stage in the program whereby there is sufficient infrastructure is made available in space, satellites around the globe who circle around, plus infrastructure on the ground which control the satellites, provide the navigation signals. Enough of that infrastructure is ready so that the system can be used. The use is still not fully 100%, hence the word initial services.
These constellations are not exclusive. Galileo will also use the GPS system for even more accuracy, and the US is tying in with the Russian GLONASS for extraterrestrial services. In other words, they will enable spacecraft to utilize the positioning system in almost any orbit around the Earth.
Some of the signals are available only during a certain percentage of the day. The satellites move around and not all of the day you have sufficient satellites inside. But there is enough to start. And this is a very important moment in the program, an excessively important moment, because this actually shows to the world that the system is really going well. The performance we actually can provide, we know, is excellent. And of course we will continue building out the full constellation, but the users can actually now start using the satellite system.
The European Galileo navigation system is nearing completion. More satellites will be launched this year, adding to a constellation which will eventually number 22.
Under initial services, there will be 3 services provided. One is the so-called open service. This is for the mass market. This is where People will use their smartphones, their navigation devices in cars, which will have Galileo-enabled chips inside, which will receive both Galileo and GPS in combination, and it is the combination of the two systems which will be used to determine the position of the user. For ESA and the European Commission, when we started with satellite navigation, it was of course not quite clear how really important satellite navigation was going to be. And we had studies, we had our insights in it, and we knew that it would be important. But now we really see how important it is, particularly looking in the future, where we're going to need to have a sufficiently developed satellite navigation infrastructure to support autonomous driving and all sorts of other applications.
NASA has already developed specialized GPS receivers for space application. The Navigator receiver from NASA's Goddard Space Flight Center first flew in 2009 and proved to be very successful. A number of future missions in HEO, GEO and MEO plan to work with this receiver using its high-sensitivity signal acquisition and tracking capabilities. NASA's JPL has also developed the Blackjack flight GPS. Now being flown aboard an Argentine satellite, the system looks at how the GPS radio signal is distorted or delayed along its path. A typical GPS signal can plot a position to within around 22 yards. Blackjack can pinpoint its host satellite continuously to an accuracy of about 1 inch. 18 receivers are on orbit, while another system under development called the Triple GNSS or Tri-G will be able to track GPS and GNSS signals, including the Russian GNSS and European Galileo navigation constellations. All of our spacefaring nations continue their Earth observation work in collaboration with a number of organizations. The refinement of orbital positioning and unhindered high-speed communications mean more new technologies craft are being added to the armada of observation satellites. They include Europe's Copernicus program with no fewer than 3 Sentinel satellite launches. In March, Sentinel-2B will be launched carrying a wide-swathe, high-definition multispectral imager. With Sentinel-2A already on orbit, both Sentinel-2 satellites will monitor land cover, vegetation and water pollution.
Now that we get Sentinel-2B to fly together with Sentinel-2A, there's a couple of improvements that we get so far. We have a revisit of 10 days. With Sentinel-2B, we will have a revisit of 5 days. That means we see every spot on Earth every 5 days. That will help, of course, also to avoid the clouds or to have the chances higher to have no clouds in the various regions of the world. Both together, Sentinel-2A and 2B will also improve the performance of the services that are using the data.
Sentinel-2B is contributing to a constellation of Sentinel satellites, which really provides data over decades in different domains and with different instruments on board. So therefore, we're building up a fully operational system, which is enough incentive for industry to invest and to rely on this information in the future.
Sentinel-2A is already supporting a lot of applications. They're ranging from, for example, agricultural applications where we can do yield forecast to forest monitoring where we, for example, see deforestation. And besides that, there's plenty of other applications like inland water where we can look at the quality of the water. We can support river monitoring, but also coastal areas where we look at the changes in the coastal regions. On top of that, we recently changed also to acquire the Antarctic region, so we're also now looking at ice and glaciers.
Later in the year, 2 more Sentinels, Sentinel-5P and Sentinel-3B, will follow. The Sentinel-5 precursor mission is a satellite dedicated to monitoring our atmosphere at a high temporal and spectral resolution. It also offers increased cloud-free observation.
A second satellite, which is a replica of the first one, is of course shorter to develop and to test. The main effort when you develop a new system is put on the first spacecraft, where you discover basically all the early problems in equipment production, software validation, integration and test. All the specifications, plans, test procedures are ready whenever you start building your second spacecraft. And this is, of course, a large benefit. The second spacecraft, let's say, was realized in 1.5 year time. The cost as well, of course, of a recurring spacecraft is much cheaper than a proto-flight spacecraft. You could say basically it's 50% of the price of the first one.
Sentinel-3B is a multi-instrument mission to measure sea surface topography, sea and land surface temperature, and ocean and land color.
We are addressing a number of issues that relate to the development of new science, but also operational missions. For example, Earth Explorer missions, the scientific missions, but also we are preparing the next generation of Sentinel missions for Copernicus. In the next 5 to 10 years in Earth observation, we will face a number of challenges, some of them coming from outside. Big data, constellations, commercial companies entering our domain. And I think there we really have to see, as ESA, as European Space Agency, a public institution, how we can best react to these external challenges and position ourselves with our programs to really address these challenges from our perspective.
Demonstrating new laser technology, ESA is launching the ADM Aeolus satellite. ADM stands for Atmospheric Dynamics Mission. It will provide global observation of wind profiles. With this mission, ESA hopes to further our knowledge of the Earth's atmosphere and weather systems. Space is a hazardous place. A key part of maintaining reliable satellite services is keeping a weather eye out. The Earth is constantly being bombarded by damaging solar storms and charged particles ejected from the Sun. These could knock out satellites and even communication systems and power grids on the ground. Geomagnetic storms, solar X-ray and proton flux, coronal mass ejections and sunspots, all are monitored continuously. The Earth is also surrounded by a cloud of debris from 60 years of human space activities, space junk which could also damage satellites. Near-Earth objects also threaten the Earth and could collide with our planet. All these threats are monitored under ESA's Space Situational Awareness Program, which the Operations Directorate hopes to see continuing to evolve.
We want to protect our assets in orbit and on Earth against impacts from space, may it be from space weather or risks from near-Earth objects. And we also want to protect our spacecraft in orbit from risk, for example, coming from space debris.
The Interagency Space Debris Coordination Committee, or IADC, is a forum of 14 nations brought together to exchange information and to research various aspects of this problem. Numerous working groups are studying methods of protection and threat mitigation. No matter what hardware is orbiting Earth, it can only make scientific observations. Only our human perception of the beauty that lies below can help us fully appreciate the planet we call home. Our seafaring nature has translated well to the space age, sailing out into the unknown in search of riches of one kind or another. While Europe and Asia continue their interest in the resource-rich moon, the United States and NASA have set their sights on nothing less than manned missions to Mars. Can they manage to go shore to shore on the most dangerous of unknown seas, deep space? With low Earth orbit harnessed, it's time to look further afield. To build a spacecraft and rocket system to reach Mars is a mammoth undertaking, but if successful, it will return the United States to the top of the space achievement ladder. The first requirement? A space capsule able to carry 6 astronauts for a long period of time and return them safely to Earth. Orion is its name, and it has flown once already in a shakedown. The next flight will be an unmanned test mission past the moon, followed by a third manned mission. The components for the vehicle are developed around the country, tested and checked, then passed on for assembly. The minutest bolt and circuit is designed, tested, redesigned and tested again. Slowly the systems come together with the aid of some breakthrough technology, particularly in manufacturing methods, new materials and processes. The first thing to notice is that NASA have gone back to the classic conic shape like Apollo, the safest design yet devised. Avionics, control systems, computer software, and a glass cockpit, all state-of-the-art.
And the concept was to go with a glass cockpit, and what that means is that the instruments are all images on a computer screen. They are all on the glass. So rather than flipping a physical switch, the crew brings up a computer screen and flips a virtual switch, a little icon of a switch or icon of a valve. And with the exception of 7 panels right around the computer screens, which have about 60 switches, that is all of the cockpit of Orion happens on the glass. One big benefit is a weight savings because you don't have to have a physical switch. And having a physical switch, not only is there the weight of the switch, but you also have the weight of the wire to the switch. And you have to have the weight of circuitry that takes that wire and feeds it into the vehicle computers.
Because of Orion's size, its all-important heat shield is the largest one ever made, and new processes were required to manufacture it.
The Orion heat shield has got to be able to withstand landing loads on the order of 300 to 400,000 pounds. Because we're returning potentially from the moon or beyond, and the flight duration from the time in which you commit to a return to the time you actually land, the weather conditions on Earth can be substantially different or difficult to predict. And so the Orion spacecraft has to be able to land in the ocean in a wide range of sea conditions, wave height, wave slope angle, and horizontal winds. That is what's driven us to a skin stringer architecture that utilizes a thick laminate composite skin bolted to a titanium substructure.
We bond on an ablator called the AVCoat. The ablator is the thermal protection part of the heat shield. The very outside of the ablator actually gets hot enough that it decomposes, and that's the ablation part of it as opposed to an insulator like a shuttle tile.
Then come the ancillary structures and equipment that will ride with the capsule. The escape tower, designed and tested, will pull the capsule away from the main rocket in the case of an emergency. Adapter separation from the rocket's upper stage. Parachute deployment. The connecting adapter to the EMS. The EMS is the service module attached to the Orion in flight, supplying oxygen, water, power and heating. Built by ESA, it is based on their very successful ATV program, which delivered supplies to the ISS. It will also provide the main engine thrust for deep space maneuvering.
We have, in particular, very tight schedule in front of us. So everybody's working under a high pressure to meet the dates, and this requires a very close collaboration.
I see a very motivated team, and so far as an agency we are quite happy with the performance of the European industry.
The US Navy is tasked with retrieving the capsule from the ocean. At first they train in the pool, then calm waters, then the Pacific, and finally the real thing. This is the RS-25, the Ferrari of liquid rocket engines and the main engine from the Space Shuttle program. Economically repurposed for the Space Launch System, 4 of these engines will power the main stage of the rocket. The main solid rocket boosters of the shuttle program also have a renewed life in the SLS. With another 2 segments added, the boosters will thrust for over 2 minutes.
This project has been a real fun effort in trying to take a heritage booster that had many, many years of reliability and great performance and evolve it into something bigger and better.
When we first undertook this design and qualification for the new booster, part of the mission was to make the booster more affordable and more modern, and of course it had to be completely redesigned for a new mission. It's a larger booster, and the mission profile is sufficiently different to where pretty much everything on the inside of the booster is different. There's well over 1,000 individual processes. Working with our customer, we were able to identify several hundred areas of improvement.
We've got totally new avionics on this vehicle versus what we had on shuttle. It's state-of-the-art.
Bigger and more powerful than any previous launch system, the SLS has been under development for some time. Designing it is one thing, building it another. In new or refurbished factories and assembly shops, the body of the largest rocket ever to fly is being constructed one piece at a time. The massive hydrogen tank takes shape. The smaller oxygen tank soon follows. The interim stage for the manned flight is another hydrogen-oxygen motor supplied by cryotanks fabricated with new technologies.
So to design and manufacture this tank, we use new materials. We process the tank by automated fiber placement. The benefit of that is we can lay down the material quickly, which provides us a low-cost operation and a very lightweight tank.
We've worked on this program for 29 months, and when we started, we'd never built a tank of this size by the methods that we did. We did automated fiber placement and fluted core, just developing the robotic fiber placement equipment and way to make the skirt in one piece was a large challenge.
Each exacting piece is fabricated, test articles are run through the mill, vibration tests, vacuum tests, acoustic tests, stress tests. Nothing is left to chance. New technology and new materials for a new generation of space exploration.
So this test, there were several things that we looked at. This was the first time we used those thermal knives to start the deployment sequence, and that allowed cut some tethers that then allowed the solar array to deploy. We wanted to test the locking mechanisms to ensure that it locked properly in space, because anything that could possibly go wrong, we wanted to see test down here so that we can ensure a successful flight.
It's all about technology. If you don't develop technologies for the future, you won't go where you want to go. So composites will decrease the weight of the tanks. It'll increase the payload performance of the launch vehicle. It'll give us, it basically enables things that we don't have today.
Soon the mighty rocket will lift human beings up further than ever before. The flight to Mars will be a long one, too long for a crew to sit in a capsule. Habitat and supplies will also be lifted to orbit and assembled. Several companies have been selected by NASA to carry out studies for a suitable system to do the job. A bit of competition is always good for invention. Bigelow Aerospace, with its Expandable Activity Module, or BEAM, currently being tested on the ISS, will develop and test a prototype of X-Base, a 330 cubic meter expandable habitat. Boeing of Houston is developing a modular habitat system that leverages more than 15 years' experience in designing, developing, assembling on orbit, and safely operating the International Space Station. Lockheed Martin will refurbish a multi-purpose logistics module into a full-scale habitat prototype that will include integrated avionics and ECLSS. Orbital ATK will mature the mission architecture and design of their initial cislunar habitat concept based on the Cygnus spacecraft that now supplies the ISS. Sierra Nevada Corporation's space systems will study and refine a flexible architecture and concept of operations for a deep space habitat that draws on the lessons of 3 to 4 commercial launches to construct a modular, long-duration habitat. NanoRacks, in conjunction with its partners, Space Systems Laurel and the United Launch Alliance, referred to collectively as the Ixion team, will conduct a comprehensive feasibility study regarding the conversion of an existing launch vehicle's upper stage, or propellant segment, into a pressurized habitable volume in space.
So if you're designing spacecraft to be in the Mars orbit, then the studies we're doing on Space Station can be applied and help us design more durable spacecraft for that Martian atmosphere. MISSI stands for the Materials International Space Station Experiment. We do study the durability of polymers in terms of their mechanical properties with radiation exposure. And we hear a lot about the radiation exposure impact on humans for flights to, say, Mars. But polymers and other materials that are used on spacecraft can also degrade from radiation, and that's one of the things I study. The MISSI 8 experiments do take a little bit of time because we do very careful dehydration measurements of the samples after they've been in space. What we found is that the Teflon erosion rate is highly dependent on the amount of sunlight and possibly the heating too. You need to know which of these environments it's going to be exposed to because it'll erode at a different rate depending on the environment.
Assembling spacecraft in orbit and fueling them for the long journey to Mars sounds simple enough. On-orbit refueling is anything but simple. NASA have been developing a system for unmanned refueling for quite some time and have a test article on board the ISS.
We can take a pick-and-place robot, put the tool wherever we need it to be, and all it needs to do is drive that tool because the smarts are in the tool. So that's what we learned from working on Hubble, is you put a smart tool with the astronauts and accomplish, both things. You've got smart tools and astronauts working together. Now we're putting smart tools with robots and trying to accomplish the same type of things we did on Hubble.
Aimed at developing capabilities for servicing, even refueling spacecraft on orbit, RRM is like doing precise surgery at a distance, doctor and patient separated by the void and vacuum of space. It's tough, but the payoff is huge.
Robotics can do things that humans can't do in terms of precision, in terms of control, holding a particular spot for 6 hours while engineers on the ground debate what to do. We can't ask a human to do that.
The robot is a very stiff, rigid interface. It's not forgiving like an astronaut's hand. So we have to take that into account. When you push on something really hard with the robot, you build up really large contact forces. When the astronaut pushes on something, his wrist might give. He's got his own internal sort of software compliance running. But in order to accommodate the robot so we don't break anything, we have to build features into the tool, features into the software. Just getting the robot to go where you want it to go, and they don't position precisely. So you have to do things like build lead-in into the tool. An astronaut could probably just get it right on there because he's right there. So we do have to do things to make them, very specific to robotic operation.
That task successful? Next stop, Mars. The first manned mission to Mars will probably only orbit the planet, checking out all the gear and processes, even launching communication satellites, and finalizing landing sites in preparation for the next mission, which will then make the descent to the surface. And that has a whole new set of problems to overcome. Unlike the Moon, Mars has stronger gravity, about 0.6 of Earth's, but it does have an atmosphere where parachutes can be used, although the atmosphere is very thin and not very deep.
Well, it's a funny thing about Mars, but if you take the average of the planet, the average height of everything in the planet, it turns out that most of the north is 2 kilometers below that, and most of the south is 2 kilometers above that. And it's just, we always land in the north because there's a lot more atmosphere. If we land in the south, it's like 4 kilometers less of air to come to a stop. In fact, at the altitude of the mountains in the south, the Mars Science Laboratory was still supersonic as it was descending into the crater that it was reaching in the north.
Assuming the need to pre-position habitats, supplies and equipment on the surface prior to a human landing, NASA and its partners are looking at several solutions. One is the HIAD, or Hypersonic Inflatable Aerodynamic Decelerator. This is basically a very large inflatable heat shield, much larger in area than the payload, able to slow the craft considerably faster than a standard spacecraft heat shield. Plans are to test the system on a payload from the ISS, utilizing a Cygnus resupply spacecraft. Once lower in the atmosphere, parachutes will further slow the payload to an altitude low enough for rocket engines to take over. Morpheus and the Zombie flight systems have matured over the last few years and are capable of delivering cargo to a planet's surface autonomously, avoiding rough terrain or other obstacles without human intervention. adding yet another building block to our human effort to explore the solar system. As the latest successes and failures come and go, Mars continues to give up her secrets. Invisible clouds are revealed with ultraviolet light, and the search for the source of methane continues with ExoMars. As we prepare to land humans on the red planet, getting there is one thing. Staying long-term is another. Can we really conquer this planet? The joint European and Russian ExoMars made a successful launch with great applause and journeyed uneventfully to Mars.
Our instrument is devoted to the measurement of trace gases by measuring the solar radiation passing through the atmosphere of the red planet.
Some scientists are trying to determine the local origins of methane gas. Is it a sign of life?
We're interested in looking at where the trace gases may be coming from. So, for example, if methane is there in abundance and you see it locally coming from a particular place, you'd like to know whether it's got a volcanic origin, whether it might be old gases that have been trapped in ice that's then released due to sublimation processes, things like that. It doesn't have to be biology. And it's important to recognize here that I'm a little bit of a skeptic. You know, I don't go for this life business. I try to keep the other guys honest.
ExoMars made a perfect orbit insertion around Mars and commenced flexing its considerable technological muscle. Returning high-resolution images and stereoscopic observations, enabling highly detailed three-dimensional maps to be created. However, the mission didn't go entirely to plan. The lander half of the probe, the Schiaparelli lander, made an ideal separation from the orbiter and commenced a textbook descent. The The heat shield functioned as expected, all systems go. The drogue chute, then the main, were deployed correctly. Then the curse of Mars struck. 1 second's worth of erroneous data was passed on to the onboard guidance and navigation control system. When this odd data was merged into the computer's algorithm, it generated a false altitude reading, placing the lander below ground level. This triggered the premature release of the parachute and back shell. Braking thrusters fired and the lander's on-ground systems began operating, thinking it had landed. Unfortunately, it was still 3.7 kilometers in the air, and the universal laws of gravity took over, the lander smashing helplessly into the ground. Satellites overhead soon located the parachute and back shell, and then the lander itself, looking like a squashed bug on a windscreen. The lander was, however, a technology demonstrator, and the problems that arose could be quickly remedied. So ESA is still fully confident of the technology and will proceed with the next lander containing the ExoMars 2020 rover. With the latest analytical technology, the rover will drill down as far as 2 meters into the Martian soil, looking for those elusive microbes. This is the Interact Centaur rover from ESA. It can be remotely controlled from orbit by ESA astronauts. NASA has its own version. They're one of the tools for future investigations on Mars. The proof of concept in Earth orbit will make it a reliable tool on Mars. Astronauts can maneuver the robot to a test table, then perform very fine operations with a number of tools and devices. It could even help assemble hardware and habitats on the Martian surface while astronauts orbit overhead. NASA's Curiosity rover continues its epic journey across Gale Crater, covering over 14 kilometers in its 3 years of operation. It will soon be replaced by its smarter big brother, Mars 2020 rover. Built on the same configuration, the 2020 rover looks strikingly similar to Curiosity, with some improvements. A landing hazard redirect feature to avoid any rocky landings, new wheels and treads for better climbing, audio microphones to hear what's going on, and a rock core sampling drill. One of the main goals of the Mars 2020 mission will be to determine the potential habitability of the planet for human visitors. Scientific instruments on board include an advanced stereoscopic imager, environmental sensors for temperature, wind speed and direction, pressure, humidity and dust particle size and shape. Pixel is an X-ray fluorescence spectrometer for chemical analysis of Martian soil. RIMFAX, a ground-penetrating radar to study subsurface geology, and Sherlock, an ultraviolet laser spectrometer for the study of fine-scale mineralogy and organic compounds. The final instrument package is MOXIE, a technology demonstrator designed to generate oxygen from the carbon dioxide in the Martian atmosphere, a critical piece of kit if humans are going to survive on Mars. It will generate oxygen for fuel and breathing. Mars's atmosphere is predominantly carbon dioxide, plus trace amounts of argon, nitrogen, oxygen and carbon monoxide. Its mean pressure is 600 Pascal, that's about 0.6% of Earth's air pressure at sea level. So another vital piece of equipment is the spacesuit.
In the future, I'm looking forward to spacesuits that are much more of a tool for the astronaut, that is more integrated with the human, and is less of an encumbrance and more of a help.
Several spacesuit designs are underway. There are many specific requirements. The flexibility to walk and move on a low-gravity planet, for example, and the ability to bend down and pick things up. They must also be able to illuminate the way forward. Ease of access for donning the suit is important, as are clearly a pressure garment and thermal insulator for the low pressure and temperatures on Mars. The latest prototypes, like the Z2 and the PXS, are going through extensive development for surface use. The Z2 meets the walking and flexibility requirements. PXS is a more traditional style of suit, but also quite flexible.
My main responsibilities on this spacesuit is the suit control assembly, and that's the box that sits right here on the front of the suit. And it allows the crew member to control their life support components, such as their cooling and their pressure, and it also controls a lot of the electronics, such as the radio and the volume, and they can see some of the data that's coming back and forth from the suit computer to that display. So one of the great things about this job is that after designing the box, I'm able to get into the suit, since it's one of the smaller sizes, and we can actually see what the limitations are, with my own hands and eyes, and not just hear that secondhand from another test subject that would be looking at the same data. And then to take that back and then to go build the next prototype and incorporate the changes that need to be made so that it works better the next time.
Another critical element for surviving on the Martian surface is power. The sunlight reaching Mars is just a little more than half of what we receive on Earth. In addition, there are regular dust storms, and solar power may not be sufficient of itself. It will have a role to play, but other sources of electric power may be required. NASA has been developing fission power plants for such requirements, working on 2 systems. The less powerful technology demonstrator unit for spacecraft and surface operations requires watts of power numbered in the tens or 100s. Kilopower addresses the need for surface power from 1 to 10 kilowatts for human habitats and scientific exploration in the harsh environments of Mars and beyond. The journey to Mars is a long one, not in kilometers as such, but where the scientific, technical and engineering hurdles that need to be overcome are concerned.
What are the things they need to know to be able to safely land, live, and return from Mars? The scientific knowledge, the technologies that we need that can make human exploration of Mars happen are within our grasp. In our lifetime, we actually can see humans land and work on Mars. A major step in this direction of planning has been the definition of what we call human exploration zones. This is a region we will land, we will live, we will use resources in many different ways, and we want to go to a variety of scientifically exciting locations. Do it in ways that humans, and only humans, can do.
One drawback: humans are fragile. To function correctly, they have a specific set of requirements: atmospheric pressure, air to breathe, water and food for nourishment, rest and sleep, and protection from radiation. Mars offers very few, but it does have an abundance of radiation. Mars habitats have been the subject of years of engineering and technical research. NASA has even thrown open the doors to students and architects to help design and develop suitable accommodation. There are minimum requirements around the number of occupants and length of stay. With limits on payload weight and mass, using local resources like sand, rock and ice to develop habitats has been strongly recommended. The 3D print competition threw up some very good ideas and designs, some of which NASA is developing further. The three finalists were Team Lava Hive, Team Gamma, and Team Space Exploration Architecture and Clouds Architecture Office of New York. Their ice house included all the components required to assemble the habitat in situ on Mars. The vehicle lands at the designated site and deploys several robots and water storage assets. The robots set about building a secure base, utilizing local sand sintered together with lasers. An inflatable plastic membrane is then deployed along with internal airlocks. The robots source local water, which is used to 3D print the inner lining of the membrane. Water is an excellent shield for radiation, and being translucent, it allows sunlight in. Hanging gardens and windows add a touch of home. NASA Langley has developed the ice dome concept from this prize-winning concept. Creating a colony on another planet really is a mammoth task. Leaving aside the training, technology and traveling, not to mention the money, building a functional, self-sustaining village will need people from all walks of life. Apart from the scientists, geologists and prospectors there to do the primary job, people will not cope with living in prefabricated temporary shelters. A town will have to be built from local resources. Engineers, builders, fabricators, electricians, plumbers and mechanics will all be in great demand. So will IT and communications experts, doctors, nurses, pilots, farmers, botanists, and the list goes on. On the other hand, not everyone gets the chance to colonize an entirely new planet, so that is one draw card. If Mars 1 is any example, it seems there will be plenty of volunteers for this dangerous work. One question hasn't been asked yet, and it's of fundamental importance. Can humans live long-term in space or on another planet with reduced gravity, less sunlight, and lower atmospheric protection? One proposal before NASA at the moment is the multi-generational independent colony for extraterrestrial habitation, autonomy and behavior, which contracts nicely to MICEHAB, and it's exactly what that name suggests. MICEHAB is a spacecraft and autonomous support system to study the long-term generational health of mice in Martian gravity. The vehicle would be placed in a stable orbit close enough to the Moon to be within easy reach by manned missions. The MICEHAB would be deployed and spun up to Mars-like gravity. It would then support the growth of a large mouse colony for a year or longer, studying reproduction and maturation of lab mice through multiple generations, which is to say, much faster than human subjects. The vehicle would house multiple levels of mouse enclosures designed to be serviced and cleaned by an onboard robot. The system would take care of feeding, watering and cleaning the mice, including their medical care. Breeding would be selectively controlled over generations in the low gravity. The mice would also be studied for any physical, behavioral or metabolic changes. The project would also collect data on deep space radiation and the hazards posed to humans. The robotic systems would also provide an in-situ demonstration of autonomous activities like maintenance for long-duration deep space missions. From time to time, astronauts would dock with the habitat to collect data and specimens. MICEHAB will allow humans to prepare to live independently from Earth in space and on the surface of Mars, and help answer that critical question we started with. Could humans survive long-term in low-gravity environments? Our solar system is vast. From our own star, the Sun, to Earth is nearly 150 million kilometers, or 1 astronomical unit. Jupiter is 5.2 AU distant, and Pluto up to 48 AU. And the solar system extends far beyond this into interstellar space. We humans cannot travel that sort of distance, at least not yet. But we can and do send our robots and probes in our place. And the results are astounding. The ion-propelled Dawn spacecraft is one of our emissaries that has rendezvoused with 2 asteroid belt objects in its multi-year mission.
The Dawn mission is one of NASA's Discovery Program missions that launched in September of 2007. So it's had a long, circuitous journey from the Earth, flying past Mars and out to the asteroid 4 Vesta, where it spent a year orbiting this small rocky object, and mapped its surface and determined its bulk composition and geological aspects of Vesta before leaving the gravitational field of Vesta and traveling for another 3 years out to the dwarf planet Ceres.
Before the arrival of the spacecraft Dawn at Ceres, we were expecting an inert rocky body.
Instead, they discovered a world of mystery and surprise. Dawn has been orbiting Ceres for more than 2 years now, providing us with fascinating views of an alien world. The mysterious bright spots on Ceres appear to be salts deposited on the surface by subterranean activity. Support for this theory can be found in another feature of interest, the bright mountain named Ahuna Mons.
We have looking in detail about the shape of the mountain, and we have compared with what we know from volcanic constructs, and we have found that Ahuna Mons' shape is very similar to that of a volcanic dome that is built by very viscose material.
When we saw Ahuna Mons, we saw that its shape was very tall. It was very tall and had steep slopes. And that reminded us of certain places in the solar system, including Earth and Mars, that had domes that were formed by volcanic activity of very slow-moving, thick material. However, on Ceres, the temperatures are so cold that the same type of magma on Earth and Mars just can't exist on Ceres. So we then concluded that the magma, or the material that's flowing on Ceres, had to be composed of mostly very salty water that would flow at the low temperatures of Ceres. And when exposed to the surface, when they were pushed out onto the surface, they would freeze and form this steep-sided dome. Ahuna Mons is unique in the solar system. There's no other place in the solar system that has a structure that matches that of Ahuna Mons, and it has to be formed by cryovolcanic activity.
Scientists at the German Aerospace Center have used stereo images to create a global digital terrain map of the dwarf planet. Another surprise, a study published by lead author Norbert Schorghofer shows permanently shadowed regions at the North Pole. These are expected to be cold enough to accumulate water ice over long time spans. Future spacecraft visiting Ceres are likely to find freshwater ice there.
So right now we are not only learning about dwarf planet Ceres, but also about planets and small bodies in the outer solar system, like Pluto and its moon. And so we are in a phase in space exploration where we are learning about a new class of objects. And we are seeing that these objects are surprising, as they have recent features on their surface. These observations tell us Ceres was active in the recent past and might be even active today. And this tells us the importance of sending a spacecraft to a dwarf planet to have a close look at the surface, as we are learning new things that are unexpected.
Dawn is now orbiting only 386 kilometers above Ceres, which is closer than the space station is to Earth. And it will continue to return spectacular views. One of the key technologies that made Dawn such a success was its ion drive.
Ion propulsion allows us to undertake missions which would be impossible without it. There have been previous missions and tests of ion propulsion to validate the basic technology, but Dawn now has made it a reality. Dawn's the only spacecraft ever in more than 58 years of space exploration to orbit 2 extraterrestrial destinations, the last uncharted worlds in the inner solar system. And it not only allows us to get to these distant bodies, but once we're in orbit, we can maneuver extensively in order to get the best possible science that we can from the mission.
Our second deep space emissary has only recently arrived at its destination, the giant planet Jupiter. Juno is our fastest probe to date. Reaching a top speed of 265,000 kilometers an hour, or 73.6 kilometers a second, it has traveled for almost 5 years to reach its target and orbits the poles of the largest planet in the solar system.
Juno's the fastest spacecraft ever to venture into the outer solar system. It's the first to orbit pole to pole about Jupiter, and it's the most heavily shielded spacecraft that we've ever launched. The mission is designed to basically wrap Jupiter in a dense net of observations, completely covering the sphere. So to do that, we need a polar orbit, one that passes over the North Pole, along a line of longitude, and over the South Pole. And we do this over the 37 orbits of the nominal mission, and by the time we're done, we've got orbits separated in longitude by about every 12 degrees. So we completely cover the sphere.
Basically, the interior of Jupiter is nearly unexplored. What we see when we look at Jupiter and all the great, amazing stuff we've discovered about Jupiter is about the moons that orbit the planet. It's about the atmosphere and the enormous weather systems and the great red spot and belts and zones, stripes across the planet, all kinds of really cool, interesting, exciting stuff, but it's kind of skin deep. When we look at Jupiter, we're going, 1% or 2% of the way down into the planet. That's what we're really seeing. Everything else about Jupiter, the deep interior of Jupiter, is nearly completely unknown.
To peer beyond the veil, the suite of instruments on board Juno includes a gravity radio science system, plasma and energetic particle detectors, ultraviolet and infrared spectrometers, and a vector magnetometer.
A magnetometer is, it's best to think of it as a fancy compass. Unlike a compass that just records the direction of the magnetic field, our instrument tells you both what direction the field is in and what the magnitude is. And we can measure that very, very accurately to 100 parts per million. Juno's magnetometer is another in a long line of magnetometers built here at Goddard Space Flight Center, following designs developed by Mario Acuna years ago. Our instrument is between 1 and 2 orders of magnitude more accurate than anything that's flown to Jupiter before. And of course, part of that is the result of the star cameras that we're able to fly with our sensors so that we can determine the absolute orientation in space of these sensors. If we did not know the orientation of the sensor as well as we can determine it with the star cameras, we would lose accuracy in the vector measurement. So we carry 4 star cameras with our 2 magnetometer sensors. These have to be held in the same orientation with respect to each other under very extreme environmental conditions. So we designed what we call a magnetometer optical bench. It's a special structure, about a square foot in size, that is made of a carbon silicon carbide material, almost impossible to machine. But once it's fabricated and the sensors are assembled, they act as one. And that's one of the reasons why we can achieve much higher accuracy than has ever been attempted before.
Studying the magnetosphere of Jupiter is a prime objective.
Magnetic fields have been a curiosity for thousands of years. And so, of course, we know now that magnetic fields are generated by what's called dynamo action, the convective motion of an electrically conducting fluid. Even though we can map the Earth's magnetic field with extraordinary accuracy with satellites in orbit about the Earth, the one thing we can't do is see clearly through all the crustal magnetization that is right beneath our feet. Jupiter is a gaseous planet, hydrogen, helium. There is no magnetized crust that obscures our view of the dynamo deep below. So the exciting part about the Jupiter mission is that we'll be able to image for the first time the magnetic field on the dynamo surface in a way that would never ever be possible on Earth. Jupiter is also the planet with the largest magnetic field. Its magnetosphere is huge. If you were to look up into the night sky, and if you could see the outline of its magnetosphere, which you can't, it would be about the size of the moon in the sky. It's a very, very large magnetosphere. In fact, in the Voyager program, we learned that the magnetic tail, the part of the magnetosphere that is drawn away from the sun, extends all the way out to the orbit of Saturn and in all likelihood beyond. It's a very large feature in our solar system. It's a pity we can't see it.
Of course, a strong magnetic field traps more radiation within its grasp, another issue for Juno.
There's two types of radiation we worry about. One is when we fly through the radiation belt, we get an instantaneous exposure, we call that flux. The other is flying through the radiation belt again and again and again gives us something about accumulation, we call that dose. And so in the beginning of the mission, we fly largely close to the planet underneath this kind of flat donut-shaped radiation belt, and then we fly around it. But eventually we fly more and more through the belts, and our radiation levels, every orbit, get worse and worse and worse. We get over 80% of radiation exposure in the last half of the mission.
For me, the great excitement is the opportunity to look down and get the first clear, unobstructed view of what the magnetic field looks like on the surface of a dynamo where it's generated. It's always incredible to be the first person in the world to see anything. We stand to be the first to be able to look down upon the dynamo and see it clearly for the first time.
Our emissary to the ringed planet Saturn is now in its final year of operation. Its outstanding performance has included dropping a probe on the moon Titan, making extensive observations of Saturn and its moons, even adjusting its mission to fly through the water vapor plumes discovered gushing into space from the moon Enceladus.
Cassini was never designed to look for life in the Enceladus ocean. But it does have powerful instruments that can be used to look for habitability. So we're looking for the conditions suitable for life. Now Enceladus is a tiny moon, but it's really intriguing. It's got this plume that is shooting out from its south pole. The plume's mostly comprised of water ice, that gets frozen when it's ejected out into space. Most of these particles are coming from these 4 major fractures that we call tiger stripes. Life needs 3 things, right? It needs water, it needs chemistry, and it needs energy. And right now, some of these lines of evidence are telling us that Enceladus has these 3 things. We see some salts, but most importantly, we see organic molecules, things like methane. We also see CO2, ammonia. One of the things that Cassini can look for is molecular hydrogen. This is the smallest molecule that exists in the universe. It's 2 hydrogens bonded together. This molecule can tell us about things like hydrothermal activity going on in the ocean of Enceladus. And this is very important as we start to answer that ultimate question of, is there really life on Enceladus?
NASA's Cassini mission has begun a daring set of ring-grazing orbits, skimming past the outside edge of Saturn's main rings. Cassini is flying closer to them than it has since its arrival over 12 years ago. It will begin the closest study of the rings and offer unprecedented views of moons orbiting near them. Even more dramatic orbits will take Cassini through the F ring, the outer and most active ring, which contains 1 ring and a spiral strand around it. Cassini will make its final orbit later this year and plunge into the Saturnian atmosphere, ending more than 11 years of scientific observations. Traveling over 10 years and 5.5 billion kilometers, New Horizons is our emissary to the outskirts of the solar system. In a dramatic flyby, New Horizons scanned Pluto and its main moon Charon. The brief encounter amassed gigabytes of data, which the spacecraft took months to download to Earth. Its close-up details of Pluto's terrain generated a great many questions. It looks more complex and highly active geologically than first thought, with solid nitrogen ice forming many fascinating and colourful textures and landscapes. New Horizons captured this high-resolution enhanced colour view of Charon just before closest approach. Charon's colour palette is not as diverse as Pluto's. Most striking is the reddish North Polar region, informally named Maunder Macula. After such a successful flyby, the mission has extended to include a second Kuiper Belt encounter. New Horizons is set to fly past 2014 MU-69, a Kuiper Belt object currently about 1.6 billion kilometers beyond Pluto. Arrival time, January 2019. As one mission ends, another is about to begin. Bepi Colombo, Europe's first mission to Mercury, is currently being put through its paces at ESA's European Space Research and Technology Centre in the Netherlands. Bepi Colombo consists of several components in a so-called spacecraft stack. Apart from the two orbiters, there's also the Mercury Transfer Module, which contains the solar electric propulsion engine to get them there.
Okay, what we have here is the MTM, the Mercury Transfer Module, which brings us, or our two spacecraft, to Mercury, the 3 xenon tanks and the 4 thrusters. And when we arrive at Mercury, this unit will be jettisoned, and then we only have our two spacecraft.
The two spacecraft are ESA's Bepi Colombo and the JAXA magnetospheric orbiter. Mercury is the closest planet to the Sun in our solar system. Yet despite temperatures reaching around 500 degrees Celsius, the previous NASA Messenger mission found evidence for ice at the planet's North Pole.
One spacecraft is provided by ESA, which is MPO, we call it MPO, Mercury Planetary Orbiter. And this spacecraft has a focus more on the planet. We want to observe the planet, do remote sensing, characterize the surface, count the craters, wanting to know about the composition of the surface, the interior of that planet. And in addition, we have a second spacecraft, and this spacecraft is called the Mercury Magnetospheric Orbiter, more focused on the environment, and this spacecraft is provided by the Japanese Space Agency.
The Messenger mission found other surprises at the smallest planet in our solar system. It discovered more chemical elements and compounds with small boiling points, known as volatiles, than expected at the surface. Messenger focused on the North Polar region, whereas Bepi Colombo and its instruments will cover the whole planet, as well as exploring its gravity field.
One of the special things about Mercury is that it's the only planet besides Earth who has a magnetic dipole field. And so we would like to understand the dipole around Mercury, or how the magnetic field around Mercury is interacting with the Sun. And that's very important for us, because then we can learn for Earth how the Earth's magnetic field is interacting with the Sun, And we have a lot of satellites around Earth which are affected by the solar wind and the interaction. So if we can get some clues about processes on Mercury, we want to learn for Earth.
Bepi Colombo's launch has been set back by minor hardware issues. Now scheduled for late 2018 launch, it is expected to reach Mercury in 2025. With the go-ahead from NASA, the Europa Clipper mission is underway, with the selection of instruments to fly on the spacecraft hopefully in the early 2020s. Its mission is focused on the Jovian moon Europa, believed to hold an enormous ocean of water beneath its icy surface. Europa's proximity to Jupiter and its speedy orbit cause the moon to stretch and contract under gravitational forces, generating mechanical heat within the core and providing enough energy to maintain a liquid ocean. Close inspection of surface areas also predicts that ice movement on the surface, similar to glacial movements, could allow for the formation of liquid water lakes close to the surface. One more place to search for those elusive signs of life. Is the cost of space exploration really worthwhile? It's a question that crops up regularly. Could the money be better spent elsewhere? Even if it were, one space program would still have to remain in place. That's the Planetary Defense Program, to locate, identify and deflect any wayward asteroid from hitting Earth and destroying our civilization. At the last count, there were 15,000 potentially dangerous candidates close to Earth. It's now over 2 years since the Rosetta mission reached its target rendezvous, 67P. It's been an audacious mission, gaining unprecedented forensic knowledge of the comet's surface, interior structure, composition and history.
We've noticed that there is not ice on the surface. We would be able to see that. At least not large patches of ice. You don't have skating rinks on this comet. And we also see gas in the coma. We see evidence of carbon monoxide and carbon dioxide and the elements themselves of carbon and oxygen in different parts of the coma.
And we discovered that this carbon was actually a very complex material, very complex carbon, very different from the simple molecules that we would expect to find there. So we don't see amino acids or alcohol or this kind of molecules which is observed in the gas, but we see something much more complex and very rich in carbon and poor in nitrogen or hydrogen compared to these other materials.
In particular, what we have observed is that the nucleus is composed of a mixture of materials like minerals, like silicates and sulfides, which have been formed in the inner part of the solar system, close to the sun.
Because the comet is kept in a very cold environment, we don't expect it to have very high temperature phases, so it can be that this material was formed closer to the sun and was then brought to the comet later. And this for us was a surprise, because we knew it for the minerals, but not so much for the organics. So it seems that the organics also can be transported over large distances in the solar system.
The most prominent, the most exciting changes on the surface, I believe it is still the big drop in the Imhotep plateau, which was 3 meters and 100 meters in height and hundreds of meters in radius. But we have seen smaller scale features like a boulder, which was at least 50 meters big, it was 10 tons heavy, which, well, on the comet is just a chocolate bar of 100 grams or so, but still it's a massive thing, which has moved by 140 meters. Likely due to activity, but we don't know the real reason.
It was time to decide what to do with Rosetta now its mission was complete. One option was to land it on the comet.
There were discussions about what would be the priority for the end of missions. So there were several scenarios put together, and one of the options was to do those very close flyovers. And I mean, in terms of the science objectives, that was the one that will bring us the more interesting scientific results. So it was decided by the science working team to go for this scenario. So yes, that's a very first, again, another first of Rosetta.
Rosetta's trajectory was altered to spiral into the comet, taking photos as it closed in.
Rosetta's blown it all open. It's made us have to change our ideas of what comets are, where they came from, and the implications of how the solar system formed and how we got to where we are today. And we've only, like Philae, just scratched the surface. And it's important to note, Rosetta mission is both the lander and the orbiter. Together, they have made it possible to do the science, to make the breakthroughs that we have. And we have only just scratched the surface. We have decades of work to do on this data. So the spacecraft may end, but the science will continue. That's what we're here for. That's what this mission was for.
We just have had a loss of signal at the expected time. This is another outstanding performance from Flight Dynamics. So we'll be listening for the signal from Rosetta for another 24 hours, but we don't expect any. And so this is the end of the Rosetta mission. Thank you and goodbye.
One major problem faced by Rosetta and its Philae lander was low gravity. When the lander's harpoons failed to secure it to the comet, it tumbled and bounced until it was lost in the rugged terrain. But engineers love a challenge, and they have already come up with a novel answer for next time. It's called the Hedgehog.
So instead, together, JPL and Stanford have been working on a totally different rover concept that is well suited to these environments, called Hedgehog. Instead of rolling around on wheels, the Hedgehog design actually puts 3 flywheels on the inside of a cube. By spinning these flywheels up very slowly and then very quickly applying a brake which transfers all the momentum from the flywheels, we're able to cause Hedgehog to either hop or tumble or perform small adjustments. So we've done many tests here on Earth in gravity offloading test beds. Recently, we have flown 2 Hedgehog prototypes on a zero-G aircraft. In these tests, we demonstrated that we would be able to perform on a comet or an asteroid. Hedgehog doesn't have a right way up. Instead, it can tumble over the surface and come to rest on any one of its faces and still work perfectly.
JAXA's sample mission from asteroid Itokawa from the last decade returned mixed results. It did, however, teach engineers and designers many lessons about the difficulties of collecting samples from asteroids. Their second attempt is currently underway. Hayabusa 2 is coasting towards another asteroid, Ryugu, and should reach its destination in the middle of next year. This new and improved robot has several new capabilities built in. They include ion engines, navigation and attitude control systems, and an explosive device to dig into the asteroid and return material from within it. Also on board are a probe and 3 miniature rovers. A secondary probe launched with Hayabusa, called Procyon, had an engine malfunction and will not complete its mission. NASA's attempt at an asteroid sample return is also underway. OSIRIS-REx was launched from Cape Canaveral Air Force Station's Space Launch Complex 41 and is on its way to intercept the near-Earth object Bennu.
2, 1. And liftoff of OSIRIS-REx, its 7-year mission to boldly go to the asteroid Bennu and back.
Bennu is a B-type asteroid of approximately 500 meters diameter. It completes an orbit around the Sun every 1.2 years, and every 6 years it comes very close to Earth. These close encounters mean there is a high probability of Bennu's impacting Earth in the late 22nd century. Bennu's size, primitive composition, and potentially hazardous orbit make it the ideal OSIRIS-REx target asteroid. It will first survey the asteroid to find an ideal touchdown site.
Understanding the shape of asteroid Bennu is going to be absolutely fundamental to understanding the geology and putting it in context. The other reason you really need to understand the topography extremely well is that when we're going in to take a sample, it's a very, very fine measurement. And so if you're coming in, you've got the sampling head at the end of this arm that has to come in perfectly square to the surface. If you don't understand shape, sort of at a 30 centimeter scale, you're not going to be able to collect a sample.
The 7-year mission will see OSIRIS-REx touch down for only a moment to retrieve a surface sample of the asteroid, then return to Earth to deposit the sample return capsule somewhere in Utah in 2023. NEOWISE has been a reliable workhorse, operating long past its planned lifetime, but its mission will eventually come to an end. Engineers estimate it will move into too much sunlight to function. However, the team is eyeing a new space telescope, one with a little more muscle. The Near-Earth Object Camera, NEOCAM, is specifically designed to hunt asteroids. The proposal has been funded for further study by NASA. Undergoing preliminary work is the Asteroid Impact Mission, AIM, whose launch could come as soon as 2020. A joint NASA-ESA project would see ESA launch AIM to a binary asteroid, Didymos, and its satellite, Didymoon. They were discovered over 20 years ago and are part of a group of asteroids called the Apollo Group, near-Earth objects that cross Earth's orbit and are a potential threat. ESA's part of the mission is to orbit and study the asteroids, in particular their orbits around each other.
AIM will rendezvous with asteroid Didymos in June 2022. The first thing it will do is to take high-resolution images so that we can reconstruct a 3D shape of the moon. And then we will use this data to test a new optical communication system with a laser transmitting these images down to Earth in a very quick way. After we do these measurements and we have the 3D model, we will sound the interior structure of the asteroid by deploying a small microlander on its surface that will emit small radio waves that will be captured by AIM and reconstruct the interior structure. After we have done these measurements, the spacecraft will move away about 100 kilometers from the system, waiting for DART to arrive and impact the moon.
NASA's contribution DART is a kinetic impactor traveling at 6 kilometers per second.
Once the impact has occurred, then we will look at the ejecta and the dynamics of the ejecta cloud. We'll come closer to the moon and repeat the same sets of measurements so that we can understand the changes in the interior structure and the shape and the morphology of the crater before and after the impact. AIM is the first mission to test the kinetic impact deflection technique. It's the first mission that will prove deep space optical communication systems, and it's the first mission to deploy CubeSats in this space and test inter-satellite communication systems. Also will be the first mission to rendezvous with a binary asteroid and characterize it so that we can understand how these bodies are formed, which is highly linked to the way the solar system has formed.
By measuring Didymoon's physical properties and its orbit before and after DART's impact, scientists will gain valuable knowledge that can be applied to a real threat should it ever occur. NASA is proceeding with long-term goals such as a manned sample return from an asteroid. A robotic spacecraft would locate and capture a small asteroid and redirect it into a lunar orbit. An Orion capsule would then rendezvous with it. Astronauts are now training and developing techniques for such a complex mission. there are still many things to be learned about asteroids and the dangers they might pose. As this animation shows, the inner solar system is awash with asteroids. Many of them are near Earth's orbit. Some even cross our path from time to time. All these possible hazards need to be identified, their orbits must be calculated to a high degree, and their threat assessed. Finally, we need to develop the technology to mitigate any danger to our planet. There are several groups of asteroids based on where they orbit. Those within Earth's orbit are Athens and Amors, while the Apollos cross Earth orbit. The majority of asteroids reside in the main asteroid belt between Mars and Jupiter. Then there are the Trojans, trapped within Jupiter's gravitational pull. And beyond that, other remnants of the solar system's formation can be found caught in the orbit of Uranus. There is a great deal more to be learned and understood about these other asteroids. To this end, 2 new asteroid missions have been planned and funded through the development stage. They will study 2 very different types of asteroid. The first of those missions is Lucy, which will visit a target-rich environment of Jupiter's mysterious Trojan asteroids. The mission will launch in October 2021 and fly by its targets between 2025 and 2033. In all, Lucy will study 6 Trojans and 1 main belt asteroid. Trojans are fossils of planet formation, and so will supply important clues to the earliest history of the solar system. The second is Psyche. This mission will explore one of the most intriguing targets in the main asteroid belt, a giant metal asteroid known as 16 Psyche. About 3 times farther away from the Sun than the Earth is, this asteroid measures about 210 kilometers in diameter, and unlike most other asteroids, which are rocky or icy bodies, is thought to comprise mostly metallic iron and nickel, similar to Earth's core. Psyche could possibly be the exposed core of an early planet, which lost its rocky outer layers in violent collisions billions of years ago. The mission will help scientists understand how planets and other bodies separated into their various layers: cores, mantles, and crusts. Psyche will map features, structure, composition, and magnetic field, and examine a landscape unlike anything explored before. For an instrument first developed as recently as the 17th century, the telescope has traveled a long way. The latest version of the once humble telescope will be going a lot farther, carrying us ever closer to the first light that ever bathed the universe in which we live. Generational change is part and parcel of our lives. In terms of space exploration, the Hubble Space Telescope has been doing its extraordinary work for a generation now, and it's time to hand over the reins.
What we've reached is the limit of Hubble's vision. As amazing as Hubble has been, we've come up against the immutable reality that Hubble can't, in fact, see everything.
Galileo, Herschel, Hubble. Our knowledge of space is marked by some of the greatest names in the human history of stargazing. But who was James Webb? His name is attached to the James Webb Space Telescope, which will soon be helping us understand what lies beyond even the amazing reach of Hubble. Originally called the Next Generation Space Telescope, Hubble's successor was renamed in 2002 to honor James E. Webb, who ran NASA from February 1961 to October 1968. Those dates, of course, put Webb at the heart of the American space program, and the moon landing in particular. But that was not Webb's sole preoccupation. Webb's energy encompassed robotic spacecraft, probes to Mars and Venus, and in 1965, his advocacy of a large space telescope. He was, in other words, a man of vision. The James Webb Space Telescope is nearing completion, in readiness for a scheduled launch in October 2018. By a happy coincidence, exactly 50 years since James Webb's tenure at NASA ended. Its aim is modest, to study every phase in the history of the universe. Several major agencies have collaborated in the creation of the James Webb Space Telescope. NASA's Goddard Space Flight Center is at the hub. ESA will provide the launch vehicle, the ultra-reliable Ariane 5 rocket. Canada's space agency is involved, as is the Space Telescope Science Institute, while Northrop Grumman is the chief contractor.
The Webb will be wonderful for the astronomy community. Not only will it give them the kinds of wonderful resolution we have with Hubble that you can get above the atmosphere, but it's going to bring them access to a wavelength region where many of them have not worked before.
We have a telescope that's far more powerful than anything that we have had before, working at infrared wavelengths, which you can't see well from the ground. And that will enable us to see things from the most distant universe that we can only guess at, things in the outer solar system that we can only guess at.
The Webb is going to be such a powerful telescope. It's going to be like the Hubble. And in the case of the Hubble, probably more than half of the greatest observations, discoveries that the Hubble made were things people didn't anticipate. I expect the same for the Webb.
The James Webb Space Telescope's mission duration is a planned 10 years, during which it has a number of specific goals to accomplish. It will search for the first galaxies, determine how galaxies were formed, observe the formation of stars, and measure the properties of planetary systems, both physical and chemical, including our own solar system. Not least of all, the Webb will carry on the task that underlies so much of humankind's activity in space, investigating the potential for life in other far-flung places. The 6,200 kilogram space-based element of the Webb will not orbit Earth, as Hubble has been doing. Instead, it will orbit the Sun. To do so, it must first travel 1.5 million kilometers, a 30-day journey to L2, the Lagrangian point at which the gravitational forces of Sun and Earth are roughly equivalent. Each orbit will take 6 months and keep the JWST out of the shadow of both Earth and Sun. Its trajectory also makes 24/7 communications possible. The Webb will stay in line with Earth as it moves around the Sun. And that is because, while the James Webb Space Telescope is looking for first light, its first task is to find darkness, a condition in which it can operate at its best. Three main component systems make up the space-based James Webb Space Telescope: an integrated science instrument model, ISM, the optical telescope element, OTE, and the spacecraft element. The key to the JWST's enhanced vision is its primary mirror, which measures 6.5 meters across. It comprises 18 segments made of beryllium, the lightest of the alkaline earth metals. A 5-layer sun shield the size of a tennis court will protect the JWST's dazzling array of specialist technology. As this orbiting infrared observatory continues the work begun by Hubble. On board are a near-infrared camera, a near-infrared spectrograph, a mid-infrared instrument, a near-infrared imager, and a slitless spectrograph. The NIRSpec has micro-shutters, which will make it possible to observe up to 100 objects simultaneously. The Webb's cameras and spectrometers are capable of detecting extremely faint signals, a crucial factor in its attempt to see as far back as first light. While NASA busies itself with James Webb, its European counterpart ESA is hard at work on another related mission with a much more famous name attached to it. Euclid is named for the Alexandrian Greek whose geometrical study, the elements, formed the basis of our mathematical thinking for almost 2 millennia.
What we want is actually to continue our successful program, which is actually providing the cutting-edge space science, meeting the challenges of worldwide research.
But where the original Euclid worked only with ruler and compass, his namesake in space will have much more sophisticated instruments in its locker. Like the Webb, Euclid boasts a modest mission to map the geometry of the dark universe. Over a period of some 6 years, it will look back over the entire time in which dark energy has contributed to the accelerating expansion of the universe. Scientists tell us that what we can see accounts for less than 5% of what is there. The rest is made up of dark matter, some 20%, and the remainder of dark energy. They act in contradictory ways. Dark matter acts through gravity to play its role in forming galaxies and slowing the rate of expansion of the universe. Dark energy, on the other hand, defeats gravity and thus encourages acceleration of that expansion. The Euclid Consortium, part of ESA's Cosmic Vision program, brings together 1,000 scientists from 100 institutes in 14 countries, with added input from NASA in the United States. In 2013, Italy's Thales Alenia Space Group was named as prime contractor, with Airbus in France responsible for the payload module. On board Euclid's payload module will be a telescope 1.2 meters in diameter, a visible light camera, and a near-infrared camera and spectrometer. Euclid will undergo its critical design review in 2017, with its launch planned for December 2020 from Kourou in French Guiana. Like the JWST, it will orbit around the L2 point. Channeling the thinker whose name it bears, Euclid will be looking for genuine insight into the evolution of cosmic structures. Investigating the nature of dark energy, dark matter, and gravity, it will track their observational signatures on the geometry of the universe and on the cosmic history of structure formation. Euclid will deploy 2 key systems: weak gravitational lensing, or WL, and baryonic acoustic oscillations, BAO. WL examines how background galaxies are disturbed by foreground dark matter and measures modifications in the shape of galaxies brought on by the gravitational lensing of dark matter. BAO reveals the wiggle patterns which help us gauge the expansion of the universe, revealing the three-dimensional distribution of structures by means of the spectroscopic red shifts of galaxies and galaxy clusters. Putting it more simply, perhaps, Euclid's task, made easier by its unprecedented accuracy and stability, is to map the shape, position, and movements of 2 billion galaxies, or 1/3 of the sky. Even more excitingly, the James Webb Space Telescope is not the only star performer, pardon the pun, on the horizon. In 2016, NASA confirmed the decision to go ahead with its Wide Field Infrared Survey Telescope, or WFIRST for short.
WFIRST is a NASA observatory that has the top ranking of the National Academy of Sciences to launch in the 2020s. It has the same image precision and power as the Hubble Space Telescope, but with 100 times the area of sky that it views.
Looking at a large fraction of the sky allows you to get a more complete accounting. For example, the stars in the Large Magellanic Cloud, which is the nearest galaxy to us, or the stars in the galactic bulge. So you can do a much more complete accounting in a much shorter amount of time.
This new observatory will offer astrophysicists the best of both worlds by casting its eye both wide and deep as it seeks to shed light on dark energy, exoplanets, and cosmic acceleration. Surveying large areas in near-infrared light, a single image from WFIRST will have all the depth and sharpness to which Hubble has accustomed us, but will cover 100 times the area. In fact, a single image will encompass as many as 1 million galaxies. The new telescope's work will slip into the groove already made by Kepler, the Sloan Digital Survey, and TESS, the Transit Exoplanet Survey satellite. WFIRST will use microlensing rather than the transit method of detection. It will employ a 2.4-meter diameter telescope provided by the National Reconnaissance Office. But the best of both worlds part of the WFIRST story comes with the coronagraph, which NASA has been able to add to its instrumental array. This is a means of dimming the light from a so-called host star in order to see better the planet or planets orbiting it. And that is highly significant if we remember that the host star may be up to 1 billion times brighter than any exoplanet identified. If successful, the coronagraph technique will make it much easier to determine the chemical composition of planetary atmospheres. WFIRST will be able to use a unique deformable telescope controlled by computer. This first mission, due for launch in the mid-2020s, being what is called a technology demonstration, laying down a scientific marker for future missions to go in even more determined pursuit of life beyond the confines of our own solar system. While all of this is going on in space, here on Earth, another agency will be tackling the question of dark matter from yet another angle. At CERN in Geneva, the Large Hadron Collider is now running at full power for the first time.
The very exciting and intriguing possibility that in addition to gravity, there might be a new force between our visible matter and dark matter, which is transmitted by a new photon-like particles, which we call dark photon or heavy photon or paraphoton. There are many different names for these particles. This experiment, it's apparatus which is about 30 meters long, and the main idea is that we search for so-called invisible decay of dark photons. And these particles could be quite light, below 1 GeV, and what is most important that these particles could be searched for at low energy experiment with fixed target experiment.
So what you see here is the beam pipe where the beam is coming. The electrons are deflected by two magnets, which are about 15 meters upstream. The purpose of that is really we need to be sure that what we get here are electrons of 100 GeV. So in this magnet, when the electrons are deflected, you generate synchrotron radiation, and this we detect with this detector here.
So the idea is that when the high-energy electron collide with the active target, which is electromagnetic calorimeter, it's create in this high-energy collision with the nuclei, create dark photons, which carry away from the setup significant fraction of the primary energy. So the experimental signature of the existence of A prime is an event with such missing energy, and we search for these events with this setup.
Might its scientists be able to replicate dark matter itself? Stars are a bit like human beings. They can be warm or cold. They come in all kinds of shapes and sizes. And, let's face it, they can be dim or bright. And recent discoveries suggest that the number of stars in our galaxy alone, the Milky Way, may exceed 200 billion. Just what are these citizens of the night sky? Days are numbers, count the stars. It's the first line from a popular song, but the one after is more relevant. We can only see so far, it says, and it sums up perfectly our relationship with the stars that matter so much in our lives. What is a star in the first place? Well, a star is to the cosmos what a key player is to a team, a ball of energy just waiting to be unleashed. Stars are essentially bodies of hot gas arising within a nebula, which itself is simply a cloud of dust and gas within a galaxy. Most famous, perhaps, is the Eagle Nebula, with its stunning pillars of creation. Each nebula is like a cosmic kindergarten, from which bright young things are just bursting to escape. We call them stars. Suggestions are that 7 new stars form each year within our Milky Way alone. What trips the wire to kick-start the formation of a star? Usually it will be one of three events. The effect of an explosion from a nearby supernova, the nebulas moving through a particularly crowded pocket of space, or a flirtation with another passing star. At some stage, an area of high density within a nebula will resolve itself into a globule of gas and dust, which will then contract under the force of its own gravity. This condensing matter heats up. As the density increases, this protostar, that is to say the first iteration of the new heavenly body, starts spinning around a central axis. A new star exists in what scientists call hydrostatic equilibrium. The inward force of gravity is balanced by the outward pressure from the star's core. If there is sufficient matter, a nuclear reaction will take place, releasing a huge burst of energy, which must find its way from the new body's core to its surface. This process takes place over an enormous time span through a combination of radiation and convection. Next time you go to the beach, imagine trying to count every grain of sand, not just the ones you see, but all the others below. Then turn that idea on its head and imagine trying to count the stars, all those we see and those we don't. ESA's Gaia telescope is making that seemingly impossible task more like a reality. Its full map of the night sky is due for completion this year, but already preliminary data covering 2 million stars has been released, and the scientific world is very excited.
We want to measure a huge number of stars, where they are and how they are moving. So we can answer two questions at the same time. What is the structure of our galaxy, but also how it is evolving, or we can also look back in time. How did the stars move to come into the place where they are now? The mission's technical measurement principle is there are two fields of view, two cameras basically looking at the sky at a very constant and fixed angle, and it rotates along the sky, so it traces a path along the stars. It then uses these measurements to determine the position of stars relative to each other, and then you can get to extreme accuracies also for the absolute position of these objects. The data comes down to the ESA antennas on the S-track network in Argentina, in Spain and in Australia. From there it goes to Darmstadt, who control the spacecraft, and then it goes to our central data processing hub near Madrid in Spain, which is an ESA center. And from there it goes to the data processing consortium, which then slices it up in different parts and processes this into science products. Our first release will contain positions of 1 billion stars. So that will allow us to look, what does the night sky really look like when you would look at in random direction with a telescope which can see very faint stars. And a subset of 2 million stars, we will have the distance and their motion. So that is really the basis for astronomical studies. People can really look into details of these sources and study the behavior of the stars. And in addition, we have light curves for about 3,000 stars, so how they have been varying over time to analyze better the internal structure of these stars.
Eventually, it will plot the position and movement of 1 billion stars in our galaxy, the Milky Way. Astrometrists still have their work cut out, but thanks to Gaia, the job of counting the stars just got a whole lot easier. Something remarkable happened in November 2016. Astronomers discovered a new way of witnessing a star's formation. Adding to the familiar methods of transit, gravitational lensing, and direct imaging, they found a new little friend, quite literally. Chandra, the world's most powerful X-ray telescope, is part of the great observatory that includes Kepler and Spitzer. It orbits Earth some 140,000 kilometers out and is capable of fine definition of hot, turbulent areas in space. Little Friend acted as a mirror, deflecting X-rays from Cygnus X3 towards Earth to help astronomers identify stars coming into being. In conjunction with the Smithsonian's Submillimeter Array (SMA) system, it detected carbon monoxide and the outflow of gases, which suggest a new star in formation. This is the first time scientists have been able to use X-rays to peer into a Bok globule, one of the focal points of star formation. The nomenclature of stars derives from their size, which is in part a function of the phase of their life they are going through. A life, incidentally, which may extend to trillions of years. The range goes from red hypergiant at one end of the scale to white dwarf at the other, smaller end. Those at the large end are far larger than our Sun. They may be billions of times greater in volume. Dwarf stars abound. The Sun is a yellow dwarf, for example, with a surface temperature of 5,500 Celsius, while red dwarfs like Proxima Centauri are stars on their way to becoming white dwarfs. What remains of giant stars whose light, put simply, is failing. The process of a star's birth culminates in the fusion of the hydrogen at its core into helium, a process called the main sequence, to which the majority of stars belong. Red dwarfs are not only the most common, they are the most durable. They burn at the low end of the surface temperature range at around 3,500 Celsius. In massive stars, the hydrogen to helium conversion is much faster. Paradoxically, the bigger the star, the shorter its life. How else are stars classified? Basically by two criteria: brightness and color. Stars are catalogued by their magnitude, either apparent or absolute. Apparent magnitude, as its name suggests, refers to the luminosity of stars as seen from Earth. This may vary, of course, according to the mass of the star itself, and especially its distance from us. Absolute magnitude corrects that by establishing the star's luminosity as detected from a standard distance. Paradoxically again, the brightest carry the lowest orders of magnitude. A century ago, working independently on opposite sides of the Atlantic, Hertzsprung and Russell came up with the same basic methodology for classifying stars within a spectroscopic range according to the light generated by their wavelengths. The scale runs from O to M, and, to cite some examples, from the blue of Zeta Puppis to the red of Betelgeuse or Betelgeuse. Made any holiday plans recently? If you're a stargazer, then NASA's own travel bureau may have just the thing for you. While a trip to another world may not be within your budget just yet, astronomers are making us increasingly aware of the heavenly bodies above us and planning on getting us there. When set alongside exotic places like Monaco or Morocco or wherever, the holiday destinations advertised in NASA's graphic travel bureau may not seem too enticing. But they are certainly, to use a travel agency cliché, out of this world. The striking images, genuine postcards from the edge we might call them, include HD 40307G. That's the very down-to-earth name for an exoplanet which astronomers call a super-Earth. One of those revealed by the Kepler Space Telescope on its so-called K2 mission when it bounced back from a mechanical failure in 2014. Could there be at least one planet orbiting every star in the galaxy? Already more than 3,000 of them have been confirmed, with almost the same number awaiting confirmation. The nearest to us is Proxima Centauri b, a mere 4 light-years away from Earth, in the triple star system of Alpha Centauri. Proxima Centauri b, excitingly, is an Earth-sized planet in the star's habitable zone, the distance at which liquid water may form on its surface.
Astronomers have found clear evidence of a planet orbiting the star Proxima Centauri. This alien world is the closest possible abode for life outside the solar system.
The idea of celestial harps is not new, but in real down-to-earth life there is indeed a harps at the center of the search for life elsewhere in our skies. It's ESO's high-accuracy radial velocity planet searcher, or HARPS for short, which is a spectrographic instrument attached to the 3.6-meter telescope at La Silla in Chile. Reflecting our connected age, in 2016, ESO invited members of the public to follow live as it embarked on a determined search for proof that circling Proxima Centauri there was, as suspected, an exoplanet, the pale red dot that gave its name to the program. Not just any exoplanet, Proxima b, as it had been labelled, is the likeliest one so far discovered with a chance of playing host to life. In late summer 2016 came the thrilling news. Close examination of the gravitational pull of the exoplanet and its wobble effect on its host produced what ESO calls clear evidence for a potentially habitable world, 1.3 times the size of Earth, and in an 11.2-day orbit around its star. Ultraviolet and X-ray radiation levels on its surface appear high, and the exoplanet is much nearer to its host than we are to our Sun. But ESO next plans to use its forthcoming extremely large telescope, the ELT, and later interstellar probes to get even closer to solving the enigma of Proxima b. Where do stars go when they die? That depends on their size, or rather on their mass. Stars of high mass will follow one of two paths. Nearing the end of their life, as the core of the star collapses, it will give rise to a supernova. The gigantic explosion triggered when the output of energy at its core suddenly ceases. Scientists are predicting that Betelgeuse, the red giant in Orion whose mass may be as much as 20 times that of our Sun, is on its way to a supernova within the next 1,000,000 years. The end product of a supernova will be either a new, different kind of star, or that great unknown, a black hole. On one hand, the core may survive as a neutron star, which may measure the remarkably small diameter of 10 to 20 kilometers. Not only that, but they are of extraordinary density. A teaspoon of their substance would weigh in the millions of tons here on Earth. Neutron stars often act as the lighthouses of the sky as well. Because of their strong magnetic field and fast rotation, they emit polar radiation beams, discernible when the beam is directed towards Earth, just as the beam from a lighthouse will be visible out at sea only in fleeting cyclical movements. The other possible fate for a dying star is to become a black hole. While there is a plurality of objects in our sky, black holes bring us face to face with a singularity, the point at which matter is compressed. The singularity will be either a point of infinite density or adopt the shape of a ring. Either way, its gravitational pull is so strong that nothing, not even light, can resist or escape it. Its boundary is described as the event horizon.
90% of black holes in the universe don't have a lot of hot material orbiting around them. They don't form these accretion disks, and so we can't observe them. Tidal disruption events, where the stellar debris causes the formation of a temporary accretion disk, offers us a way to probe this population of supermassive black holes.
One tool astrophysicists use to stare into the abyss is X-ray reverberation mapping.
X-ray reverberation mapping has been very successful at probing the accretion flow in well-established accretion disk structures, but had never been used to look at tidal disruption events. My collaborator at the University of Maryland and I were having lunch one day, and she says, "Has anyone ever looked at tidal disruption events with X-ray reverberation mapping?" That night, I stayed late at the office and just tried it out on this data from Swift J1644, and much to my surprise, the result was amazing, and I could see that we were looking at the structure of the inner accretion flow around a normally dormant black hole for the first time. It's not like a normal accretion flow in an active galaxy that's a flat disk. This is something that is extremely puffy, very turbulent, and we are measuring flashes of X-ray emission deep within this newly formed accretion disk. Previously, astronomers had thought that the X-ray emission is coming from far out in a jet. But what we're finding with these observations is that the X-ray emission is coming from flares very close to the supermassive black hole. And we can use these observations to probe properties of the black hole itself. For instance, we found that the mass of the black hole is something on the order of 1,000,000 times the mass of the Sun.
The Milky Way, which contains our solar system, is itself part of a so-called local group of galaxies, including, for example, Andromeda, which in turn belong to the Virgo supercluster, 100 million light years across. When we've had a bump on the head, we say we're seeing stars. Looking at it from an astronomical point of view, the number of stars out there is enough to make anyone's head spin. And that's before we even get to the dark side. Perhaps that American politician was right. There are indeed things we know we don't know. For instance, cosmologically speaking, we know we don't know much, and certainly not nearly enough, about two of the enduring mysteries of the universe, dark matter and dark energy. It's little wonder that scientists are devoting so much grey matter and energy of their own to finding out as much as they can. Seen any big birds recently? Ice Cube has. If you think that's a cool name, you're right. Ice Cube is an observatory at the South Pole, and it saw Big Bird back in December 2012.
Ice Cube is a neutrino telescope located at the South Pole, or to be more precise, under it. It consists of over 5,000 detectors that are spread out into a cube about a kilometer on each side. It's the world's biggest and its coolest telescope. Ice Cube has detected a handful of extremely energetic neutrinos. One of them, which is called Big Bird, has an energy of about 2 peta-electron volts. To give you an idea of how much energy that is, it is about 1 million times the energy of a dental X-ray.
Scientists have been using the names of critters from the popular TV series Sesame Street to designate major events that may help us better understand the particles that emanate from space. Particles like neutrinos.
So a neutrino is an incredibly small particle. It moves almost at the speed of light. It is nearly massless. It's incredibly plentiful, but it's very, very hard to detect because it will not interact with just about anything. If you could detect them though, because they have traveled through the universe essentially undeflected, they have information that you could not access in any other way.
The theory is that neutrinos are caused by violent events in space. In 2012, light from such an event began reaching Earth. This was a year-long outburst which happened 10 billion years ago in the unromantically named galaxy PKS B1424-418.
What we have been able to establish for the first time is an individual blazar as a potential birthplace of an individual neutrino. The Fermi Gamma Ray Space Telescope has an instrument called the Large Area Telescope, which we use to monitor the gamma ray sky, the highest energy electromagnetic band. And we just noticed that there was a tremendous increase in the amount of gamma ray light coming from this one extragalactic blazar. A blazar is an extremely powerful, variable galaxy that is powered by a supermassive black hole. It went up not by a little bit, not by a few percent. It went up like 15 to 30 times its average flux. So we knew something was afoot. Later on, it turned out to be coincident both in time and in space with the neutrino that was detected by Ice Cube.
Working in conjunction with NASA's Fermi X-ray telescope, Ice Cube was able to link the cosmic neutrino it observed with that outburst from the gamma ray blazar. The first time such a causal link between neutrinos and a single extragalactic object had been established.
The enormous increase in gamma ray flux seen by LAT and radio flux by other Tanami telescopes let us finger the exact blazar which is responsible for Big Bird. This is the first time that we can point and say that blazar is where this neutrino came from.
Neutrinos and gamma rays are what Fermi is all about. It has already made some startling discoveries. One of its latest is finding the most distant and oldest blazars. Blazars are a type of galaxy whose intense gamma-ray emissions are powered by supersized black holes. These distant objects emitted their light when the universe was 1.4 billion years old, or just 10% of its present age. That they developed so early in cosmic history challenges current ideas of how supermassive black holes form and grow. Fermi has received an upgrade to improve its capabilities.
We see gamma rays, which are the highest energy form of light. And with each object that we see these gamma rays from, what we're doing is exploring some of the places in the universe with the most extreme environments.
The kinds of objects that we can study are pulsars and neutron stars, black holes, as well as dark matter.
So, to analyze these events, we have written a very long and complex program that basically uses all the information that was recorded by the instrument and figure out what is the direction of the gamma ray, its energy, and whether or not it's a real gamma ray and not a charged cosmic ray. So obviously software is really important for the LAT.
The software that we use to analyze the LAT data has gone through many revisions over the course of the mission. But PAS-8 is really the first revision of the software where we took into account all of the experience that we gained from operating the LAT in its orbital environment.
PAS-8 has made everything better, but one of the things that it's made better is that it's allowed us to open our gamma ray eyes to higher energies before, so that's a completely new view, and it's allowed us to open our gamma ray eyes at energies lower than before, so that's another completely new view, in addition to improving everything across the entire energy range.
The improvements that we've made to the software retroactively apply to all the data that we've collected. And so these improvements significantly enhance what we can do with the data that we already have, as well as the data that we'll collect.
Fermi's talents have also been concentrated on the search for dark matter, and in doing so it has observed unusual behavior in objects that remain unexplained. For instance, Fermi has discovered a gigantic structure in our galaxy, with what looks like bubbles extending above and below the galactic center. These are enormous gamma-ray emitting lobes. Each lobe is 25 light-years tall, and the entire structure may be only a few million years old. Within these clouds, extremely energetic electrons are interacting with low-energy light to produce gamma rays, but no one knows the source of these electrons. When studying these massive objects, scientists must look at the other end of the size spectrum for answers. Those at CERN in Switzerland are expecting great things from the Large Hadron Collider, after it too received an upgrade, an increase of power by 40%. In its new improved form, it is due to produce far more data than it previously did. The LHC has already revealed the Higgs boson particle. One of two types of fundamental particle, fermions or the other, in our standard model of the universe. What other secrets might it be about to unearth, as it were?
With an increased luminosity, we gain sensitivity at the highest energy. So suddenly we will explore energies that hitherto were not really reachable. So if new physics is hidden there, this is the chance to see it. Some indications that created a lot of excitement with the theorists were seen with the experiment as there may be fluctuations, there may be real particles. As a physicist, of course, I hope that this is new physics already. But maybe that would be too simple.
The Higgs boson was the last puzzle piece in the standard model of fundamental particles and the forces which govern them throughout the universe.
What we really want is to understand the universe and why it looks and acts the way it does today. Our role as particle physicists are to figure out what the elementary particles are and how they fit together and interact, kind of like puzzle pieces, in the way the puzzle pieces fit together to give us a picture of the universe. Over the last 120 years or so, we've discovered all the individual puzzle pieces that build up to give us a theory called the Standard Model, which is kind of like the picture on the box. But we know that it's an incomplete theory. What we've essentially got is a small section of a puzzle picture that fits together very nicely and gives us all the particles that we see today, but we have no idea what the bigger picture is. The Higgs boson that we discovered in 2012 was the final piece in our Standard Model puzzle, and it was a fantastic discovery because it completed that small picture. And now what we can do is possibly use this Higgs boson to access the other parts of the puzzle. So our Higgs boson becomes like a Rosetta Stone to talk between the Standard Model particles and these new, what we call dark sector or hidden sector particles. So we're going to need to create many, many more Higgs bosons to be able to start seeing hints of this. And that's where the higher energy is useful. When we go to higher energy, it's almost as if we're getting a microscope to look on what we've discovered so far. It's possible that there are some very small differences in that Higgs boson, like the way that it decays, that we haven't noticed yet because we haven't had a strong enough microscope. But with a higher energy collider, with the LHC running at 13 TeV, maybe that is going to give us a strong enough microscope so we can see some small differences between our Standard Model theory and the Higgs boson that we have today. And maybe that'll give us some hint of some new physics that we can expect to come.
But it doesn't explain why nature prefers matter to antimatter, or what dark matter is. One theory that has been developed to answer these questions is what is called supersymmetry.
So one of the problems that supersymmetry could resolve is the mystery of dark matter. So this is something that astronomers and cosmologists tell us that there's an additional source of gravity in the universe which cannot be attributed to things we can see, stars, the nebulae and other things like that. And so at the moment this has the mysterious name dark matter. I think that's at least partly because we don't really know what it is. It's quite reasonable to think that it's a particle of a kind that we could potentially produce at the LHC, and supersymmetry, or at least some forms of supersymmetry, could explain that matter and predict its properties. So the main problem, if you ask most physicists, I think, that supersymmetry would explain is the mass of the Higgs boson. With the Standard Model as it stands, we cannot explain why the Higgs boson has the mass it has. It should be many times heavier than it actually is. So heavy that we would have no chance at all of seeing it in any foreseeable experiment. And this currently has no explanation. Supersymmetry would provide a very neat solution to that problem.
So, does dark matter? It certainly does. It makes up about a quarter of the universe. What is it? The short answer is, we don't know. The phrase was coined in the 1930s by Swiss scientist Fritz Zwicky. 4 decades later, Vera Rubin's studies of galaxy rotation confirmed his thinking. Galaxies have more mass than observable light would lead us to suspect. One suspect suggested by supersymmetry are the neutralinos, sometimes called WIMPs, or weakly interacting heavy particles. These particles act as their own antiparticle. They annihilate each other and release a flurry of secondary particles and medium energy gamma rays.
The LHC experiments are very capable to find dark matter. If, for example, supersymmetry is the symmetry which nature has realized, then I'm very, very confident that maybe even very quickly we can find, with the LHC experiments, supersymmetry. And that would be great. I mean, imagine we have taken roughly 40, 50 years in order to find and to really discover the Standard Model of particle physics. But that only explains 4 to 5% of the energy and matter density of the universe. I think LHC is the right machine to bring the first light, to shed the first light into the dark universe. There are more and more connections between space research and particle physics, but on the methodology, for example, and such things, but also on the science itself. There is a very strong connection, especially through dark matter. I mean, astronomers and astrophysicists will tell us in the next, 10, 20 years with their new telescopes, they will tell us how dark matter, for example, has shaped the universe. And with the LHC, we will find what type of matter that really is.
These are some of the things we know that we don't know. But what if new physics tells us there are things we don't know that we don't know? The latest LHC data has turned up some interesting results.
In the data we took last year, we started to see a clustering of events, of diphoton events with 2 photons at a particular region of mass. The significance of that is not at this point very high. With more data, we don't know what's going to happen. There's a chance it could stay, but there's also a bigger chance that it will go away again. But which is going to happen, we don't know.
Physicists are keen to explore any glitch in the data.
The most exciting thing would be to find something that is completely outside the standard model. Even if it's just a hint that there is something more within our reach, just to give us an idea of where to look for new physics. There's got to be something out there. We know that our picture is incomplete, and we just have to find the right place to look for it.
For this year's running, we are running again at 13 TeV centre of mass energy. But the big difference this year is we're going to run at a lot higher intensities, and we expect to get a much bigger data sample. So the experiment itself is ready and starting to take the data that's coming, and it really is shipshape waiting for the new data. At that point, of course, then we're looking in great detail and great depth at the data to try and understand what the physics is in the new data. And there's many different things we will be looking at with this new data sample. We will look again at the known processes of the standard model, which we've already seen at lower collision energies, and we started to understand and to measure with last year's data. But we'll also, of course, look hard at places where we might be able to see new physics starting to occur.
From the tiniest of subatomic particles to the immensity of galactic clusters, scientists and astronomers are looking into the past so as to see the future.
But when you think again about what we're exploring, when you think about the images that we're going to take, when you think about how far away and how far back in time we're going to look, you can't help but feel like you're a part of something that's really important, that's helping us see not just about the past of the universe, but the past of us, where we've been and really where we're going to go.
If discovering the true nature of dark matter is successful, then we will have put together a picture of about 30% of the universe. There's still a lot more stuff missing, and it's called dark energy. Scientists have labeled dark energy one of the biggest mysteries in physics. Dark energy is the name attached to the force that appears to account for as much as 70% of the universe. Our fixation with dark energy dates from the late 20th century, when Hubble's brilliant revelation of supernovae showed us that the universe, approximately half its lifetime ago, was expanding more slowly than it is in our time. It started to speed up around 7.5 billion years ago. Why? Dark energy is the working name for the amorphous answer to that specific question. Is it a property of space itself? Does empty space contain its own energy? Does that energy increase as more space comes into existence? Dark energy has negative pressure. As dark matter is inimical to light, so dark energy repels gravity. At least that's how the theory goes. And to back it up, one major international effort is nearing the end of its scheduled working plan. Begun in 2013, the Dark Energy Survey, or DES, is an international project linking 400 scientists from 25 institutions in the United States, Australia, Brazil, Spain, the UK, Germany and Switzerland. Its chief instrument is a 570 megapixel digital camera, DCAM, attached to the Blanco telescope at Cerro Tololo in Chile.
I'm a member of the Dark Energy Survey Collaboration, and I'm here on Cerro Tololo working to help commission the new dark energy camera that we've just installed on the Blanco telescope. The whole purpose of our project is to understand what is dark energy. Dark energy was discovered just less than 15 years ago, actually. In fact, using, in part, this very telescope. And it was discovered by its effect on the universe. So dark energy is our name, and it's just a name that we give to the phenomenon that's causing the universe's expansion to accelerate.
We're not trying to figure out if dark energy exists. We're not trying to find it. We know dark energy exists. We're trying to characterize it. We're trying to understand what it does to us, what it does to the universe, to its expansion rate, and to the gravitational attraction of things like galaxies. Over 5 years, the Dark Energy Survey will scan 5,000 square degrees of sky, far back in time and far away from us, in order to measure the distances of supernovae and the distributions of galaxies.
In some sense, the purpose of our experiment and what we'll learn by understanding more about what dark energy is to find out about the fate of the universe. What is going to happen into the future? Is the universe really going to keep expanding faster and faster and faster, or not?
Covering 5,000 square degrees of southern sky, the DES project is due to complete its search in 2018. Like the DES, some other exciting discoveries lie potentially just around the corner. While space-based telescopes continue their tireless scouring of the skies, their ground-based counterparts are poised on the brink of a dramatic new age. More than 3,000 meters above sea level, at Cerro Armazones near Paranal in Chile, ESO's ELT, that's Extremely Large Telescope to you and me, is nearing the start of its working life. With its stunning 5-mirror system, its diameter is an unprecedented 39 meters, making it the largest optical and near-infrared telescope in the world. Extremely large telescopes are currently one of the highest priority areas of development in ground-based astronomy. On ESO's ELT's job list will be the continuing search for exoplanets, examining the possibility, for example, of establishing contact with Proxima Centauri b, one of the likeliest candidates for Earth-like biological conditions. The ELT, attracting 15 times more light than the largest telescopes in operation today, will help detect water and organic molecules, a major step forward in our quest for extraterrestrial life, and make possible direct measurement of the speed of acceleration of our universe's expansion. Will it provide some of the answers we seek? Or will it show us collectively that we don't yet even know what we don't know? Is gravity an illusion? Do we need a new theory of gravity on a cosmic scale? As Einstein himself observed, the most beautiful thing we can experience is the mysterious.